Testing. Okay, welcome all to the 10th edition of PriSC. We have a pretty exciting program lined up for you today. We're going to have sessions on secure compilation, of course, hardware security and timing state channels and more. But before we get started, I would like to, we have two quick announcements. There's going to be a lightning talk session in the afternoon. You can basically pitch ideas or like share exciting news with the community. If you'd like to use this opportunity but haven't signed up for it, please let me or Leslie know. You can come to us during the break. Second announcement, there's gonna be a workshop dinner tonight at 7 p.m. at Crêperie Les Pieds de Bleu. It's only 10 minutes walk from here. It's pretty easy to get there. You can find like directions online, but it shouldn't be hard to get there. If you haven't signed up though for that and you still would like to join, that's okay, but please let us know. Now that I think most of us are here, I would like to introduce our keynote speaker, Samuel Gross. Samuel is a security researcher at Google Project Zero. He works on browser security, finding bugs that could put millions of users at risk. Before that, he led the development of the V8 sandbox. This is a super important mitigation in the V8 JavaScript engine that prevents bugs from turning into critical security vulnerabilities. Samuel, take it away.
Yeah, thank you. Is the microphone working? Cool, perfect. Got some technical issues. Let's hope they resolve. But yeah, thank you for the introduction. My pleasure to be here. Thanks for bringing me here. So yeah, my name is Samuel. I work at Google. As you just said, Marco, I worked in the V8 team until kind of mid last year. And then I moved back to Project Zero, which is the security research team in Google. But kind of the common theme is that a lot of my time I spent on trying to make JavaScript engines more secure. And so this is kind of what I'm here for today, specifically to talk a bit about the V8 sandbox, which is like a sandboxing, in-process sandboxing mechanism we're building for V8. Yeah, I guess the story I kind of want to tell is how V8's approach to security moved from basically kind of just trying to write correct code to still trying to write correct code, but also building these special mechanisms for kind of containing vulnerabilities at runtime. Yeah. I want to start with a bit of motivation, kind of why are JavaScript engines a relevant topic, security of JavaScript engines, why is that relevant? So here I have a bunch of headlines from kind of go back 10 years, the oldest one you see is on the left in the middle from 2016. And these are all kind of, the same kind of headline, right? Some browser got exploited, there was an attack in the wild, and all of these were vulnerabilities in the JavaScript engines. So yeah, it's really kind of a focus for attackers to look at these engines and find vulnerabilities there and use them for these kinds of targeted or semi-targeted attacks. So yeah, here we are looking at kind of 10 years of JavaScript engine attacks. Yeah, so I think that raises a few questions. Maybe one question would be why, what's so special about JavaScript engines? Why are there maybe so many bugs, or why do they get attacked so frequently? So for that, to explain that, I want to start with something that's not JavaScript. So here, this is some C++ or C program that I made up. You see this function get, which returns a value in an array. It gets an integer index passed in, and then it returns that element. It does attempt to do some sort of bounds checking, right? So you see there's an if condition. However, this isn't quite working because the index is assigned integer. right? And so if you give it a negative number, this like bounce check thing would succeed. It would say, yes, this is fine, but then it actually does go out of bounds right afterwards. And so if an attacker was able to reach this function with their own controlled index, this is how they could cause memory corruption. Now, this type of bug is well known, right? Like we know this sort of problem for 40 years or so, and we kind of understand, like this is a solved problem in some sense. Like the compiler can fix this for you, right? So if you think of memory safe languages like Rust or Go or Swift or Java or whatever, they don't have these problems. And like the reason for that basically is that in these languages, the compiler also inserts a bounce check before every memory access, right? And so in the compiler, kind of what it would do as in one of the earlier phases, it would add these its own bounce check operations before every access. And then if they fail, they might terminate the program, like, you know, a Rust panic or something. But it like terminates in a controlled way. It's not memory corruption. Now, what happens if our program is actually correct, right? So in this case, all I did was change this signed integer to an unsigned size t. And now this works correctly. Now this bounce check is actually correct. So what happens now? Well, first, the compiler still does the same thing. It still adds its own bounce check to protect this memory access. However, later on in its optimization phase, the compiler would realize, you know, oh, there's actually no way I could get to this bounce check with I not being in this range, right? And so it can prove that this check is redundant and it eliminates it. And this is actually quite important for performance because it means like a lot of these bounce, like a lot of the memory safety kind of comes for free if the compiler is able to prove that the access is indeed always safe. Right, and so with that, let's take a look at some JavaScript example. I promise this is the only JavaScript you have to read today. This is like somewhat similar, right? So we have also an array object and a get function that takes an index, but now it also takes some like multiplier, some m value, and it multiplies the array element with that multiplier. Yeah. Again, here we have a bounce check, so actually we also like one that should be correct, right? So we check if it's less than 0 or if it's larger or equal to the length, and then we do this access. So let's take a look at how a JavaScript compiler would deal with this. So one of the first things it does is, and this is true for pretty much all compilers, it would convert it to its own kind of intermediate language that it knows how to optimize on, right? Most of this is not like particularly JavaScript specific, except for the speculate instruction at the start. Because as you will see as you can see in the JavaScript code, there's no type information for the compiler, right? It just gets I and M. It doesn't know if it's integers or whatever. And so the compiler kind of based on previous executions, it has to speculate about types, and then it has to guard against the speculation becoming invalid in the future. And so for this case, it might have seen that in the past, I was always like an integer, like a SMI. SMI is like small integer. So it would speculate that I will continue to be a SMI in the future, and it adds the speculate operation, which is nothing more than kind of a, is this an integer? If not, like bail out, go to the interpreter or something. But from that point on, it's kind of, it looks like kind of regular intermediate language code maybe. So we have the bounce check, right? We have the two-number conversion, and then like there we also have this bounce check added by the compiler, right? Before the array access. Because JavaScript is supposed to be memory safe, so yeah, you need some sort of checking there. Now, like, okay, now we do actually kind of the same thing that our previous C compiler or C++ compiler did, which is that we realize, okay, actually there is a check for I, and it cannot be that I is, you know, not in this range at this point in time. And so, okay, we again eliminate this bounce check. The problem is there's something in between. There's a two-number conversion in between, and that is something that is not side effect free, right? So in this case, Here's an example where an attacker could abuse this to cause memory corruption, because in JavaScript, the to-number conversion, that's a very complex operation that can potentially trigger arbitrary code to run. So in particular, if you give it, if M is an object that has a custom value of method, which is used for converting to primitives, then this method will be invoked during to-number, and it can resize the array, right? And in this case, it might resize it to 0. And now we have a problem because we eliminated this bounds check thinking that I is always in bounds, but actually we did the bounds check against the length 100, but then at the time of the access, the length is 0, right? So this doesn't work. And so we have kind of done the same thing, but now it's insecure, and it's actually the cause of memory corruption and not the fix. So, so yeah, I think maybe another way to try and explain why JavaScript engines are a bit special is by thinking of kind of the technology stack that makes up a typical application. So if you think of something like an image parser maybe, that is also exposed to untrusted data, the technology stack might look like Simplify, but it might look something like this, where, you know, the bottom you have the hardware, then you have the compiler and runtime that compiles the code of the image parser, and then the data is consumed and is processed by this code. And in terms of the attacker model, you have the attacker controls only the data, so only the image that goes in. And the code is like written by a trusted developer, but it may have bugs, right? And so that is the attack surface. But the compiler and runtime are kind of one step removed, and so they can guarantee memory safety at this level. So why do I say one step removed? So if you compare this to a JavaScript engine, the picture looks a bit different, because there, the like the code for the compiler, so JavaScript or WebAssembly, they are directly attacker controlled, and they also operate on attacker controlled data, like, you know, runtime object and that sort of stuff. And so in this model, the compiler and the runtime are directly the attack surface. And this makes it really hard to guarantee memory safety at that level, because any bug there is potentially a memory corruption problem, like we just saw. Right, I mean, maybe another way to think of this is that, you know, you could imagine, or I think it's quite likely, that compilers like Rust or Go or so, these compilers probably have bugs, and these bugs would lead to insecure machine code being generated. But they don't really matter, because to trigger these bugs, you have to give the compiler like malicious Rust or Go code, and then execute the result, at which, like, this is just not an attacker model, right? Like, if the attacker can run arbitrary Rust or Go code, like, what do you want? And so this is kind of a fundamental difference in the JavaScript world. To make this point a bit more clear, this is a slide I made 3 years ago. I'm not gonna walk through all of this now, but there's a talk you can watch. What I'm trying to do here is, oh no, hope it comes back. What I'm trying to do here, yeah, perfect, is kind of show how different optimizations in the compiler, come on, come back. Sorry. Okay, let's hope it sticks. How different optimizations lead to different types of memory unsafety issues, right? So the red circles, they are the types of memory unsafety issues we kind of commonly have, like type safety and maybe spatial memory safety. And then there's like lots of these optimizations that a compiler would do, like common sub-expression elimination or loop invariant code motion, these sorts of things. And then like there's different bugs that are like these CVE numbers that happened in these phases, and then you can kind of trace these nodes and edges. They form kind of a path of how did this specific bug end up leading to memory unsafety, right? And so you can, for example, see there's this one here, like there's bounce check elimination. There was a bug in the bounce check elimination logic. While you can easily imagine how that leads to memory unsafety, right? Like if the bounce check is wrong, it straight up goes out of bounds. Less obvious are kind of these ones down here or here maybe, where like kind of a subtle logic issue in some analysis further away leads to confusion of other optimizations, which then like maybe confuse like yet another thing, and then ultimately they also end up causing maybe an incorrect bounds check, or like the length of an array to be incorrectly set or something like this. Yeah, I guess what I want to say here is that it's not the case that you have this one type of bug in the compiler that always happens. It's always like this, just this one type of issue. It's really kind of the whole picture of there's a good chance that a logic bug in any of these optimizations, there is some way where that can lead to memory unsafety later on in the compiler. And so yeah, this is where this is from. Okay, so we've kind of answered now, so why are JavaScript engines relevant? Why are they kind of special? Maybe what's still a bit unclear is why are there so many problems, why are there so many bugs in these engines? And I think that is also relatively simple maybe. I like the way I would explain it, it starts with the requirements. So we want our browser to go fast, we want these engines to go fast, we want the code to run fast. So we have these performance requirements. And this is kind of in combination with a very complex and evolving spec. So JavaScript is really kind of a terrible language to make go fast, but then we want to make it go really fast. And so this creates a lot of friction. And so this pretty much directly leads to a very complex code base, right? So if you want JavaScript code to run really fast, well, you've got to do all of these optimizations, you've got to do these speculations on types, all of this stuff. So you end up with a quite complex code base, which means that if you work a lot on this complex code base, the language is evolving, you're implementing new features, you are implementing new optimization, you're going to make mistakes and bugs are going to happen. And kind of as we just saw, like every logical error in a compiler or runtime, there's a very good chance that it actually also is a security bug, because there's some path where it ends up leading to something unexpected. So this was kind of the motivation and background maybe. What can we do, right? So how can we make this a bit more secure? And I think for that we can kind of look at the same picture and try to see, like, is there any one of these steps that we could break? We could start here, right? And we could rethink, do we actually need to make these things go fast? It's maybe not the most relevant question for this audience, but let's dive into it a bit. Like one option here is disabling optimizing compilers, right? So in these JavaScript engines, you have typically a lot of compilers. You maybe like in V8, JavaScript gets compiled through 4 layers of, like, there's 4 different compilers or execution tiers. And the question is, could we just disable kind of the heavyweight ones to reduce some attack surface here, right? So this, this works to some degree, right? So you can get maybe like a 50% reduction. We have this spreadsheet which is public on kind of bugs that we know are exploitable, and there we have a few properties that we track. For example, would disabling a compiler have mitigated this bug, right? And you see, like, this column here. There's green and red in here, so it's kind of 50-50. Maybe like half of the bugs are in these optimizing compilers and the other half are elsewhere. But of course, this can come at a dramatic performance cost, right? So it can be anywhere from 5 to 90%. Like, really depends on the workload. If you have a static web page, well, I mean, you're not really going to notice. If you have some, I don't know, maybe like Photoshop in the web or so, this exists. It needs heavy optimizations to work smoothly or at all. Like there you will definitely notice. I guess what I would say is, okay, like maybe it's 50% bug reduction, so this is good. This is a useful tool. One thing to keep in mind is kind of bug count is a metric, and I guess what you actually more care about is like something like, users getting harmed or attacked by by exploits. And these are not the same thing, right? So if you reduce the number of bugs by 50%, that doesn't mean that there will be half as many attacks, because that would assume that every kind of attacker just has one bug, right? And that's very unlikely to be the case. They typically have more than one bug in their repertoire. So I would say this isn't the solution, but it can be a useful thing to do. Okay, let's look at the next kind of chain here. Once the projector comes back. Should I?
The live stream still works, so I think.
Okay. Okay, so it's just the projector maybe rebooting or something. Anyway, I don't, like, the next slide is not super full of anything. I can just go on. So the question was basically, can we kind of prevent that these performance requirements lead to a highly complex code base? Yeah, it would be.
It's pretty turned off. That's
Is it restarting, or what is it doing? Sorry.
we're not supposed to start with the projectors like that.
Okay, it's back. Thank you. Perfect.
Just in time.
Exactly. Exactly. This is actually all just planned. I'm just like rewriting the slides now. This is but okay, no. So yeah, I guess again, like the kind of this is here. Here's where we are, right? So can we prevent this from happening? Oh no! What? Oh.
gonna have like a 5 minutes break, so they have time to restart it. And there's some problem with the frequency of the projector, it seems. So like 5 minutes break, and hopefully we will restart. And sorry about that. Okay, cool. It looks like we're back live. Fingers crossed. Go ahead.
Okay, perfect. Okay, thank you so much. Right, let's do a like very brief recap, right? So this is where we are. We kind of investigating what can we do based on kind of this flow diagram. Yeah, can we somehow avoid like the requirements leading to a complex code base, basically? Like it seems difficult, right? Like I think like just based on the fact that you're trying to make JavaScript, which is like has this hugely complex spec, and you're trying to make that go fast, I think there's like a baseline level of complexity that you will struggle to get below, basically, and that baseline level is still way too high. I mean, I think there are examples. This is a blog post from last year where V8 is trying like fairly big changes based on the thinking that this should reduce complexity to some degree, right? So this is a major refactoring where the optimizing compilers in V8, they are moving away from a sea of nodes representation, which is kind of, you know, all of these operations, they just kind of flow. You have a big soup of compiler compiler operations, and then you like use that as your intermediate representation. And then they're now moving to kind of classic control flow graph based IR, because basically what it says here, like the sea of nodes turned out to be too complex. It adds even more complexity. So there is some examples for this, but I think there is a baseline level of complexity, and that is still too high. Right, so next step would be somehow avoid code complexity leading to bugs, right? So this is, I think, what most people would intuitively go for. I mean, yeah, in theory, we know how to write correct compilers, right? In practice, bugs happen, right? Like testing and fuzzing are definitely crucial. Like one of the main fuzzers that V8 is using is this Fusilli, which is also open source. Like they do work, they do find a lot of bugs, but there is also kind of a ceiling to what they can achieve, right? Like at some point we looked a bit into kind of what is the rough level of complexity that these fuzzers can trigger, like can find, and there's definitely a lot of bugs that are just basically too complex. Like you need, I don't know, 15 different pieces to come together to trigger the bug. And for the fuzzer, it's just too far away. It'll like the kind of the search space of all possible JavaScript programs is just so astronomical big that a fuzzer is just not going to cover a relevant part of it ever. I guess what I would say is that like this is a big hard problem, right? Like writing bug-free code in a complex code base, that's a big complicated problem. And the security strategy should not be, yeah, we just write bug-free code, fingers crossed. That's not going to lead to a great outcome. So kind of like I guess one other option that maybe goes into this this space here is can we do verification, some sort of formal verification or whatever, and basically look at maybe what the compiler produces and try to prove that this code is correct, right? I have an example here for how that might look in practice and why it is hard. So this would roughly correspond to quite heavily optimized version of this JavaScript code, which just kind of sets a property of an object to the result of some function call. So the register RAX is object A. The way so if a like proper JavaScript optimizing compiler optimizes this code, roughly what it ends up doing is first it needs to check what A is. So this is kind of the same thing I described before, where the compiler would look like how did this function get called in the past, and it would see, okay, maybe A was always a certain object of a certain type. And in V8 these types are called map object. Like a map is kind of a type description object for JavaScript objects. And so the compiler would insert a type check that would look like this, where it looks at like, is the kind of first pointer in this object, is it this pointer? And then I know the type. Don't get confused about the -1. The -1 is because V8 uses tag pointers. So every pointer has a 1-bit set, which indicates that it's a pointer and not an integer, which means if you dereferences, you always have to subtract 1, right? But it's basically just looking at the first pointer in this object and seeing if it is this type that it expects. So at that point, okay, if this passes, if it gets through that, it knows the type of A. And then it does, like I'm reordering the things a bit, but it does 2 loads. So it loads the B property and it loads the bar property directly from memory. Then it calls this built-in. So here, like foo might be some function implemented in the engine itself, like a kind of standard library function or something like that. And then it directly stores the result back to C, right? So this would roughly be what a proper optimizing compiler does. If you try to verify that this code is correct and it doesn't do anything fishy, you'll probably have a bit of a hard time. So, I mean, here this is the kind of reasonable. Like to prove that these memory loads are correct, you have to go into this map object and also like parse the type object, this map object, and like verify that, you know, offset 8 is really property B or so, and offset 12 is property bar, and so on. And you kind of need to have some trust that this stays this way and it doesn't like later change, but otherwise, okay, you can kind of do this. Where it gets much more complicated is down here, where basically down here and down here, where basically, like for this store to be safe, there's a lot of assumptions that make this store correct. And so these assumptions are, for example, that the compiler can prove that, like there's maybe runtime information that tells the compiler, you know, property B of an A object is always this specific type, right? And so then it doesn't need to have a type check there. But also, you need to trust that the compiler's like side effect modeling is correct, because the compiler here definitely assumes that this built-in function doesn't have side effects. Like if the built-in function could run JavaScript code, we would be kind of back to the early example that I had where like you might change the type of these objects might change during foo. And then again, the store is not safe. So basically here you need to make a lot of assumptions or basically trust the compiler that it did the right thing, which is not what you want to do if you're trying to verify the result of the compiler. So yeah, this seems difficult, seems hard. Okay, so with that, that kind of brings us to the last thing. Can we somehow do something about this? And this is basically the idea that we had, and this is the idea behind the sandbox, is to basically decouple correctness from security, right? So we kind of concluded, okay, it is really hard to guarantee that we will always be correct, but maybe there's something we can do to not have every correctness issue be a security issue. And so, yeah, this is the sandboxing approach, right? So we accept that bugs will happen in this environment, but then we want to contain or limit what these bugs lead to. And specifically what we want to do is we want to have like, so what you see on the right here is kind of the user space of your process, and we divide that up into a sandboxed, like a part of the address space that is the sandbox, and like the privileged rest. And then we want to make it so that all of these correctness bugs, they all just lead to corruption inside the sandbox, but they don't kind of corrupt memory elsewhere, like they don't spread to other parts of the process. I guess in an ideal world, like this would mean that in sandbox corruption is purely a correctness issue. Like this would be the ideal outcome. It seems a bit unlikely that we'll get there anytime soon, but this would be the motivation, right? Yeah, let's construct this. Let's see how this works under the hood. Basically, we take our user space, address space, and we take a huge chunk of it, maybe 1 terabyte. This is very cheap. On every modern operating system, virtual memory is very cheap. So we can just do that. Now this 1 terabyte is where all of V8's objects go. All of these JavaScript objects, the JavaScript arrays, these type information objects, everything that V8 operates on, it's all in this 1 terabyte region. Now, okay, what you're going to have is like references between these objects, right? So you have maybe one object has a property that points to another object. Pre-sandbox, this would have been just a raw 64-bit pointer. But that is not compatible with the sandbox model, because if you have a 64-bit pointer and there's memory corruption and this pointer gets corrupted, then it could point anywhere, right? It could point outside the sandbox space. And if it then gets used in any way, like you would corrupt memory elsewhere, which is precisely what we want to avoid. So instead, the way it works is all of these pointers, they all become offsets, right? So in this case, for 1 terabyte, they would become 40-bit offsets, and then they would have to be added to the base address of the sandbox to be used. Which then means, okay, if there's memory corruption and this 40-bit offset gets corrupted, doesn't really matter because it can only ever point inside the sandbox still. Now then, the next kind of challenge here is that there's also external objects. You have maybe a V8 object that references a DOM node, like a HTML element or something like that. So that HTML element, that's a normal C++ object on the C++ heap, not in the sandbox. And so again, pre-sandbox, this would have been a raw pointer. Again, this is not safe. And so instead, for those objects, we have an indirection. So in the sandbox, you just keep a maybe 32-bit index. That indexes into some table, and that table has the pointer and type information. And this is actually really, really similar to how like a Unix kernel, for example, works, where the index is basically a file descriptor, and it goes into a like table in privileged memory, and then that points to something. Right. So this is kind of the idea: get rid of all the raw pointers. In practice, it looks a little more complicated because everything is complicated in V8. But this is more closely to how it actually looks like today, where there's actually different types of tables, just because there's very different types of external objects. So for example, you have like machine code should also not be in the sandbox. Like the raw JITted code lives in its own trusted space. And for that, there's a dedicated table that basically has the signature and the pointer, right? So you want to make sure that if you call a piece of machine code, that you call it with the right signature, because otherwise, like, stuff can go wrong. So there's a dedicated table for that. There's a similar thing for kind of trusted V8 objects. Like for example, there's JITted code also has metadata that is needed for de-optimizing code or like kind of managing code. And this metadata also must not be corrupted. So that must also live elsewhere. And so then there's a dedicated space and table for these trusted V8 objects and so on. But roughly speaking, the picture is kind of this of like offsets in the sandbox, indices for everything else. So what I just showed, this is kind of how it looks today. In the future, one thing that I'm quite excited about is there's a potential for hardware support for this, which would, then it would really be very similar to how user space and kernel work, where if you run sandbox code, you somehow drop the CPU's privileges, so it really cannot write to out of sandbox memory, and it can only write inside the sandbox address space. This would be built on top of like the software sandbox, which does all of this separation of objects, and it would add kind of a layer of security. I guess here the ideal final outcome would be that V8 would be comfortable running untrusted machine code in their sandbox. Like you give it machine code and V8 is like, okay, fine. I like put the CPU in the sandbox mode and then off I go, and this is fine. Again, this is not going to happen in the near future, but this would be the inspiration, let's say. I guess with that, so if you think about this, like I would call this maybe Sandbox version 2, like with hardware support. What it would mean is like you kind of split up your code into something you consider privileged code, which would be kind of kernel space, which can read and write everything. And then this must be careful or ideally like memory safe in some way. And then you have sandbox code, which can only write in the sandbox. And ideally, this is like where bugs no longer matter. And so if you think of V8, like V8 has a lot of different types of code in it. Kind of this is how it would probably be partitioned maybe, where the important bit is like this here, right? So all of the like JIT generated code, all of the interpreters, all of that stuff, this is where all of these bugs happen. All of this code runs sandboxed. And then on the other side, you have what cannot run sandbox is binding code, which is the kind of glue code to the rest of the process, to like the rendering engine and so on. Like this cannot be sandbox because it needs to integrate with out of sandbox objects. And then like you could maybe run actually the compiler itself in sandbox mode. It just seems like that would be a lot of work with very limited benefit, because the compiler is not actually corrupting memory. It's the code generated by the compiler that's corrupting memory. So that's what you want to run sandboxed. Maybe coming back to this picture I had at the start, maybe kind of the way to think about it is if you add sandboxing, you do again get some sort of like additional layer that's one step removed from the direct attack surface to protect your application. Cool. So I think that also already brings me kind of towards the end. So this is really the idea, right? So the sandbox, what it wants to do is decouple correctness and security in such that, you know, maybe generated code, it can still be incorrect, but at least it's secure, right? And then with the sandbox, these security properties are actually easier to verify. One example is since maybe, what is it, like November or so last year, there's now a bytecode verifier for V8. So this is the initial, like if you take JavaScript code, the first way it's going to execute is in an interpreter that runs custom bytecode. And this bytecode can now be verified to be safe to execute, right? And this is actually really simple in the sandbox model. So if you're interested, take a look at this document. But it really just boils down to like checking that the bytecode doesn't kind of do incorrect jumps and doesn't access registers like out of bounds. Like it's kind of really just two properties that you need to prove to be sure it's sandbox safe. Versus if you try to prove that the bytecode is correct, you would be looking at quite a big pile of work because there's all sorts of kind of subtle invariants that need to be correct for it to not corrupt any memory. Coming back to this code verification example, I want to show how this suddenly transforms to a much easier problem in the same way. So again, this was the example I had before of this function that like loads some properties, calls a built-in and stores a property, where we concluded it was kind of, it seemed hard to generically validate that this is always correct. So let's look at how this changes with sandboxing. The first thing that changes is that I said we can no longer have raw pointers, right? So these red instructions, they would no longer be, like we wouldn't compile our code in this way because we no longer have raw pointers. Instead, the code would look something like this on the right, where we are actually loading like 32-bit offsets from memory, and then we're adding them to the sandbox base. So maybe in this example, the sandbox base is always in register 13. I think that's actually exactly how it is. Like in V8, I think RS13 is always the base. So we are already paying like a little bit of a price here by having an additional instruction. But this would be the code that actually the compiler generates now with the sandbox. And so let's now this is actually quite a kind of a simple problem, because all we have to do to verify that it's sandbox secure is we have to validate that all the pointers point into the sandbox. But this is basically trivial because we always have 32-bit values that we load from memory. We add them to the base. And so there's no way this can be not in the 1 terabyte sandbox, with the assumption that R13 is correctly set. But okay, like that is one assumption we have to make. The second thing we have to prove is that all the offsets are inside, like are kind of less than the guard regions around the sandbox, so they cannot like reach out. In this case, this is also trivial because all the offsets are constants. It would get a bit more complicated with, like if you had dynamic indices, then you probably need some sort of additional clamping instruction, but that's also doable. And we do need to validate that kind of the jumps go to right places, but this is also doable. So I would say what we've achieved here is that with the sandboxing model, our code is actually much more amenable to verification for these security properties of the sandbox. Okay, where it's at, so where we today, so the software-only sandbox is mostly finished and it's shipping in Chrome. Like the design level issues are mostly taken care of. There's like implementation issues remaining, by which I mean that basically what happened is, well, we added a new security boundary kind of in the middle of V8. And so now there was a lot of like code written pre-sandbox that was not safe anymore, right? Because it would make assumptions of the form that, you know, if I store something in the sandbox and then later read it back, it would be the same thing, but actually that's not true. So there was a lot of code that had to be like rewritten or at least refactored a bit. And there's still some remaining issues like that. Yeah, the sandbox is part of the bug bounty program already, so if you find any issues, you can get money for it. And we do have a prototype for hardware sandboxing. It's based on like Intel's memory protection keys, which are not really made for this purpose. It's kind of misusing them, but it does work with some limitations, but it does work. Much more interesting is ARM's upcoming POE2. So that's a similar like processor feature for kind of basically adjusting memory permissions at runtime in a more fine granular way. And this is really, like this looks like it would be really powerful for this use case. Yeah. What's left to do? There's actually kind of a lot of things that I think would be worth doing. I mean, the code verification is kind of one obvious example. We haven't actually built it, right? We have only so far been spending all the time building the infrastructure for the sandbox, but not actually building this verification on top of it. It would be worth, like there's still going to be a lot of C++ code that is privileged in some sense. So it would be worth investigating or investing in memory safety features for this like privileged code. Yeah, more hardware sandboxing work should be very useful. I mentioned there's these trusted spaces in V8 itself. So there's like bytecode or code metadata, they live in trusted memory. So there's room for hardening this trusted memory space. And then also like sandbox fuzzing is, I think, also an interesting topic to work on. Right, and that brings me to the end. So quick recap, what I've tried to explain is how compilers exposed to untrusted code, how that very quickly means that any correctness bug is also a security bug, and guaranteeing or proving correctness of one of these kind of complex real-world compilers is hard. And so instead, the idea behind the sandbox is to decouple correctness and security. And this is the goal, and this is what it tries to achieve. And I think this is a plausible path to actually getting a secure and high-performance engine at some point in the future. Great. Thanks a lot, and I'm happy to take questions.
Yeah, we already have a couple of questions, and we have the another microphone that's going to run around. First question maybe here, or yeah.
It seems that the kind of memory protection that you're looking into is similar to what is provided by Sherry. What are your thoughts on that?
Yeah, I think it would work. Like you could take Cherry's hardware features and like build this sandboxing like this. I guess it, yeah, I don't know. Like we haven't looked into building this ourselves. Like we focused on, like we mostly focused on ARM because that's where the customer base is right now, right? Like it's mostly Android phones that that would benefit from this. But I think it would be definitely a good research project. Maybe there was actually someone looking into this, but I think, yeah, it would be worth looking, like how can you make Cherry and make it work with this model? Absolutely.
Now that the sandbox is rolled out, did you actually see the number of exploits go down? Or has there been any kind of evaluation? How much it is helping?
It's ongoing. So like the story is a little more complicated. So we already shipped the sandbox in 2021 or 2022, I think. But it was like a really early version. Like the sandbox, what we didn't want to do is basically spend 5 years of engineering to build the sandbox and then launch like a massive change all at once, because that's going to be horrible. So it's actually all been kind of built in production, like while it was already shipping. I would say the sandbox has been kind of in a beta, I would call it, since like last year. The way we track it is basically this here, like this spreadsheet. Like you can look at this. Yeah, the link is up there, but I'll post the slides. Or if you just search for this, you should find it. But we do kind of keep track of what are V8 bugs that we know are exploitable. Like we have a program where if you can write an exploit for a V8 bug, even if it's not your bug, even if you didn't find this bug, if you write an exploit for it and can like compromise a like server that we host ourselves, then you can get money for that. And this provides us with like a nice data set of these are bugs that were actually exploitable. And this is one way we do try to kind of quantify the impact of the sandbox. I think if you look at this now, you will see some sort of drop from 2024 to 2025. The sandbox probably has some effect on that, but it's not like, I would say it's like the progress bar is kind of here. Like I think it's going to be more interesting to see what happens when it gets to actually this point here, where like we still know of a handful of issues ourselves that we haven't gotten around to fixing. So I think that will be like the point in time to really check, did it have an impact on this data?
Thanks.
You focused a lot on JavaScript. What are your thoughts on WebAssembly as another source of bugs in the browser?
Yeah, so I mean, what I would say is WebAssembly seems like a much better language for this sort of application, because as I said a few times, right, like JavaScript is just so terrible for optimizing because everything can change all the time. And WebAssembly is much more strict, right? Like you have actually type information in the code. Like the compiler has a much easier job optimizing things. So I think it's the right, the better language for this purpose. What we have, so WebAssembly is like WebAssembly launched like 2017 or so, right? But that was a very simple version of WebAssembly. Like this was basically like what would now be called linear memory WebAssembly, where you really just kind of have like arithmetic operations, and you have load and store from like one big array of memory. And this was quite simple, and we didn't see many bugs in it. What happened later is, I think, maybe 2023-ish, what was called WASM-GC launched, which is a very harmless name for a huge bag of complexity, because WASM-GC basically added like a highly complex object model to WebAssembly. The goal was that you wanted to be able to compile maybe Java or like other languages that have like a garbage collector maybe. And so to make that possible, you needed to make WebAssembly much more complex and give it like an object model, like hugely complex type system, garbage collection support, and so on. And then we definitely saw like a huge bump in vulnerabilities caused by the additional complexity. I would still say WebAssembly is the better language, but it's not like it has, on some sense, it has caught up a little bit to JavaScript in complexity.
Just as a very quick follow-up question, to what extent can WebAssembly live in this sandbox?
It fully lives in the sandbox. Maybe if I show this slide also again, like all of WebAssembly's objects are also like this, right? So they all live in the sandbox itself, and also the linear memory WebAssembly, like these huge like raw memory areas, they also are just buffers in the sandbox space. Where it does create some friction is that if I show this slide again, like WebAssembly adds a bunch of objects here, right? Because WebAssembly needs like kind of management objects that describe the state of the WebAssembly virtual machine, and like, you know, where does execution continue later on, or where's my stack, or this sort of stuff. So it does increase, I would say, the attack surface. But yeah.
Thanks for the great talk. I wanted to ask about this bytecode verification. You mentioned that you could do it, but you don't yet do it. Is performance an issue, or like when would you even do bytecode verification?
It's a good question. So like where do I have it? So it's a bit unclear. Like we are currently experimenting with how we like run it, or when we run it. Like if it turns out to be like to not have much of performance impact, we would just run it all the time. The alternative would be you could do like stochastic based verification, like you could say verify 20% of the bytecode or something, which would mean that if there's a bug that leads to invalid bytecode, then there's an upper bound on the reliability of an exploit, which is whatever, 80% or 90%, which would be sufficient to heavily discourage real attackers from using them. So this would be enough. But like it's like the way to measure this is a bit slow, because you need to like you do like A/B trials in production on like stable population, and then like first you need to write the code, then you need to wait until the code ships in like Chrome stable. Then you need to do these experiments, you need to ramp them up like over time, like from very small populations. So it all takes a bit of time, but it's ongoing. Or like it would also be something like if you have, like I mentioned, there are these kind of settings for like more secure browsers, right? Like maybe there's a setting to disable optimizing compilers. Like you could also imagine that enabling all sorts of verifiers would be an option that a user could toggle if they choose.
I also have a question. Yeah, thank you. I also have a question about the type of attacks that are still possible. So it sounds like, okay, now the memory within the sandbox can't be trusted, and this could lead to data-oriented attacks. And some security researchers say that these are equally, if not perhaps like worse than corruption. So I was wondering, like what are your thoughts about that?
Yeah, I mean, so what I would say is one thing that makes the normal JavaScript bugs really attractive is that they are very powerful. Like if you take these compiler bugs that I showed at the start, like they give an attacker a lot of flexibility to control kind of exactly when and how and what memory gets corrupted, right? So this is really powerful, and this leads to really reliable exploits and attacks. And so the with the sandbox, the hope or the goal would be that you take these really reliable, powerful bugs, and you contain those, and what you then end up with is kind of a lower quality for an attacker type of bug that is less reliable and harder to exploit, right? Because maybe you could imagine, like what you said, now you introduce like C++ kind of maybe data races, right? So this is one type of bug we have seen a lot, is like double fetch style bugs where C++ code reads a value from inside the sandbox once, then does something, reads it again, and implicitly assumes that it didn't change in between, right? And if it did, it like goes out of bounds or something. But these bugs are certainly of kind of lower quality for an attacker, because they don't give you the same level of flexibility. And they are also kind of mitigatable in more generic ways, right? So if you think of, like if you actually did write this code in a memory safe language, this bug would go away. If you use maybe like memory tagging, like hardware security features, they can actually mitigate these like lower quality, like classic bugs. So this is the broad idea, like that these bugs are of lower quality. It is definitely true that we have had a lot of also high quality sandbox bypasses, which is why I'm saying it's still not quite where I want it to be, right? Like there is still, like for example, a high quality bug in the sandbox attacker model would be that you maybe are able to jump to a piece of code that isn't like what you expect it to be, right? And you run custom machine code. But it just seems like that attack surface is significantly smaller than all of your compilers, right? So yeah.
Thank you. Any more questions? If not, let's thank Samuel again.
Thank you.
We originally we should have had a talk on information flow control now, but we had like some technical issues earlier, so we decided to move this talk, efficient dependency resolution in IFC, in the afternoon. We are gonna update the schedule. It's gonna be at the end of the day. So this ends this session. So we're early for coffee break at 10:30, and see you later at 11. Thank you.
Detecting undefined behavior across Rust FFI.
Attending this talk. I want to start with an apology actually. Like if you hear me slowing down with voice, it's because I haven't slept for 24 hours due to weather and flight canceling and finding trains and places to come here in time. So yeah, without no further ado, so today I'm going to talk about how to detect undefined behavior in Rust FFI, our approach, and possible other problems that the research community can still tackle. And then what's a talk about Rust without talking a little bit about C first. Also, as a note, this is a work in progress, so we just have few preliminary results. There's still plenty of stuff to do. Would really appreciate your feedback and maybe potentially searching for collaborations. Okay. Right, so we've been programming for a few decades now. Great, we have C that has given us amazing systems, large-scale systems. Most of the systems we have today are written in C, and despite decades of fantastic research going into how to verify C, we are still troubled by lots of memory safety issues. So then, inspired by the verification community as well as by the language designers and advancing languages, we have now safer languages such as Rust and Spark and so on, which promise us a slightly safer, better world when building systems. And for that, like perhaps one of the most popular in the last decade or so has been Rust. There has been a lot of encouragement from both academia and industry to actually slowly move towards these safer languages. A lot of adoption in industry, which led subsequently to quite a few works, again, both in industry and academia, that tackle the translation from C to Rust. So there's a lot of different works at the moment tackling C to Rust translation. They come with different Take the normal microphone for
Yes. Yeah, we'll probably.
Oh,
hang on.
works. Okay,
Turn down the volume.
thanks. All right. So as we are moving from C to Rust, there's also we have a new set of memory safety issues now because we have two systems written in different programming languages with two different memory models that have to interact in what we hope it's a safe way. So then we have new works that aim to actually make this make sure that the bridge between Rust and C is safer. Now, are we safe at this point? Lots of work done to become safer. We have a totally and completely new class of issues and memory safety issues that we have to tackle now. So we have Rust and C. They often, they work with different memory data layouts representation, different alignments. Interpreting one data type written in Rust differently in C can definitely lead to undefined behavior. Then you have error handling in Rust, which is used with a dedicated data structure. And in general, in C, you use numeric opcodes or global states and so on to denote errors. Misinterpreting those numbers in Rust can also lead to undefined behavior. Then you have panics and unwinding. So Rust treats panics quite nicely. Once you have panics, it unwinds the stack for you, and trying to do that while having a call into C, which doesn't do that, can again lead to issues into C, which does not expect the stack to be unwinded. So you might end up in an inconsistent program state. Then of course you have lots of synchronization issues because the concurrency models are different. And then you have like the bread and butter of Rust, which is memory ownership and lifetime. So in Rust, a value always has one owner. There's no such thing as ownership or lifetime in Rust. So lifetime represents the lifetime of a reference. So a reference is similar to a pointer, but you have some additional constraints in Rust that are enforced by the type checker. Then you might have undefined behavior that leak across boundary. Those might also affect Rust safety. And then you have very strict aliasing model in Rust, which again is not enforced in C. So we go towards a safer world, but now there's a new class of issues that we need to tackle. So at least for the type mismatch, we have quite nice bindings these days that make sure that the types are aligned. But for memory safety, we don't have that much tool support at the moment to ensure that the strong disciplines in Rust are actually enforced by C. So it's actually, we go back to being the developer's responsibility to avoid undefined behavior in FFI by maintaining Rust types invariant. So we kind of go back, but not really back, because what Rust still allows us is to kind of minimize the space in which these issues can occur. So yes, we can still have undefined behaviors and issues and memory safety issues, but the search space for detecting these issues is much smaller these days. All right. So there's quite a bit of work for verifying and detecting undefined behavior in unsafe Rust. There are amazing tools and even theoretical frameworks. Many people know of Rustbelt, PriSC from Aeneas, Crusoe, Kani, Mirai. So there's plenty of tools that are allowing us to offer a framework for verifying or checking undefined behavior in unsafe Rust. But this is just unsafe Rust. What I'm building towards is Rust plus C. So we need to somehow extend these technologies to also interact with C contracts or with C behavior. Then for bug detection tools, we have MIRI, which is the most used bug detection tool for unsafe Rust. So MIRI is an interpreter that implements the stack borrows discipline. So what's a stack borrow discipline in Rust? It's a model that allows us to define the aliasing discipline in Rust and checks whether any of the unsafe code violates these disciplines. So that's great. It's highly used. There's a database of all the different bugs and issues that MIRI has detected, so very practical. However, it does not extend to C. So again, we stay only in the Rust world. There was an effort a couple of years ago to extend MIRI to C by working at the LLVM level, and that has produced good results. However, it's really slow since both MIRI and MIRI LLI are interpreters. They assume a good test suite in order to function properly. All right, so this is kind of the background so far. Let's see quickly what are the safety pillars of Rust type system. So let's consider this very simple three-liner program. what I mentioned earlier is that every value in Rust, every value in Rust has one owner. So what that means is that at any one point, any value can only be is owned by exactly one variable. So that variable is the only one that can say deallocate or free if heap is involved. Heap that free that memory. Then we have another thing specific to Rust and few other languages, which is mutability. So you can explicitly mention whether the value can be mutated or not. You also have borrowing, which is slightly different than the pointers in C. So borrowing, the first borrowing in the second line, it's a read-only reference. So it allows us to read, it creates a reference to that memory location with read-only permission, as well as reading with mutability permissions. Now, all these together, these disciplines form the core of Rust memory safety by abiding to these safety principles that combine the few disciplines. So the first safety discipline, as I mentioned, is that every value has a single owner. And second one is that the lender needs to outlive all of its alive references. So there can be no reference pointing to something that no longer exists, in other words, so that avoids dangling pointers. Then a mutable borrow can only be created if its lender has no other borrows living. So that's in general, at least in the concurrent setup, is to avoid two threads to say, avoid data races, like two threads modifying the same value at the same time. And finally, the lender cannot be modified as long as one of its shared borrowers is still alive. So in other words, at any one point you can have multiple shared references, but exactly only one mutable reference. All right, now let's go back to C and look at a very simple program. We have a function, add1, a method that simply takes in a reference to an integer and increments it by 1. So simple, we expect here to, given this program, we expect here to be, this line to print 42. Now the equivalent Rust program would be written as so. However, if I'm just passing this to Rust, just to exhibit a little bit the mutability, Rust will complain at this point because I only gave an immutable read-only permission. So I'm not allowed to mutate. Super great, the compiler complains you cannot do that. And in order to mutate, you have to change and add a mutability annotation. Now, what happens if instead of doing that, I'm simply adding, I already have a library that adds one defined in C. I only have one library. I already have a library that does the functionality I'm searching for, namely adding one. So I'm doing that, and as you guess, nothing actually happens. I can compile and run this just run this program, and I'm expecting here to have to print 41 because I know that I cannot be mutated. Yet if we run this program, we will have 42 there, which is a very simple undefined behavior, but with complicated paths, this can lead to pretty much a lot of undefined behavior and chaos. So this is the sort of problems we are trying to tackle, like how to enforce that the type disciplines of Rust are actually respected by C. And to complicate things a little bit further, as I mentioned earlier, only the owner can free memory. But if you're calling functions, if you're calling into C, and C does not have the notion of ownership, it could be that on a certain path you will have a free here, while what Rust does once P goes out of scope, so so what does it mean? That once the owner goes out of scope of some value allocated on the heap, that value will be automatically freed. So what happens here is that there will be at one of the intermediate representation, the compiler inserts a free and will free P. Well, that has also been freed on a certain path in the FFI. So at this point, you could have a double free on a certain path. Right, so to go quickly through our solution for this problem. So we are trying to use the type information that we have. So Rust has a very rich type system information. And we're thinking, can we leverage this type information somehow to check whether there's any violation of the expected behavior by the set function? So we take the type information and we translate it into a dynamic test and then just test whether that value is as expected, right? So in this case, say I have, I'm creating a copy of the value that was stored in I, and I'm just checking whether the value that I points to is the same as X. So this looks a little bit naive, and it will be difficult to extend to other properties, say beyond mutability, if I have something like aliasing and so on. So instead, what we do, instead of just checking the execution effect, we actually check what happens at each step in the execution. How do we do that? We actually have an interpreter already that does that, which is MIRI LLI. So what we basically do is we use the type information to generate a property-based test. Why a property-based test? Because that allows me to fuzz through a lot of different values. Then we use MIRI to guide the execution towards the FFI call, at which point we use MIRI LLI to check whether the property in the PBT is as expected. Okay, so how is this different than MIRI, LLI, MIRI PBT, so many things? Well, what MIRI does in order to check for an undefined behavior, if this is a Rust crate, it quantifies over the entire, like it tries to capture the execution of the entire crate, assuming you have a really good test suite that is able to quantify over the entire crate. While MIRI LLI does exactly the same thing, hoping that at some point it hits the FFI, right? Our goal is to, instead of doing this big search space, is to reduce the search space to only this hot area where we note that some issues might happen. So that's basically the goal of MIRI PBT. And we have some preliminary results. We tried to run MIRI and MIRI LLI on the same data set. There were no new bugs there, but once we tried and we introduced some random freeze or some random operations inside the C call, MIRI PBT was able to find almost all the bugs, while MIRI LLI was not able, because it's not able to quantify over the entire space, search space of C. Okay, so our goal with MIRI PBT was to find undefined behavior in the Rust C FFI, and we do that with, our aim is to reduce the human effort by reducing the number of test cases. This has been developed by colleagues at TU Delft, Julius and Jana, and we want to do way more than that. We have a static analysis plan that is quite long, and I don't have time to go through it, but I'm very happy to explain why we need a static approach, and finally not a static approach, but a hybrid approach where we do both static and dynamic checks. And with that, I conclude.
So
Thank you.
Are there any questions? Oh, by the way, can the next speaker try to prepare herself or himself? Who? Question?
Thank you. Quick question, I'm not quite sure. How do you invoke the FFI if you don't go through a test from the crate? How can you be sure that you supply correct parameters that won't just crash the FFI because of violated invariance?
So that's a great point. First, yes, it can crash without the proper, if the types, like it can be in an inconsistent state. And indeed, so we are still using MIRI to reach that state. So we are still crafting a test suite to reach the FFI, but then inside the FFI we need nothing. So that is automatically generated. So there's still, okay, and there is where actually the second part of the static analysis comes into play, because the static analysis is supposed to collect all the constraints that allows me then to fuzz through the context. So I fuzz the context, and then I fuzz the FFI, and but I happy to chat more during the break.
One more question?
Who was?
Hello. Hello. Oh.
I'm happy to.
I was going to ask you to go back a few slides.
Oh, sure.
But if we don't have time, I can ask you offline.
I can definitely join you with my laptop offline, or if I can answer without the slides, I'm also happy while they install.
I was just wondering, in the example, the add one
Yes.
thing, and you had star I.
Yes.
Can't the compiler optimize that and assume that no
Yes.
one has modified I since you haven't
Exactly.
given?
That's the problem. Exactly. The compiler uses that information to optimize the program, and subsequently leads to undefined behavior if actually the C function is modifying.
Yeah, but so does your assert EQ actually do anything then if the compiler optimizes?
Again, please.
I'll talk to you offline.
Okay, sure. I have to pass you this, I think.
So let's thank the speaker again. And now the next speaker is Brianna Marshall for specifying ABIs with reusability on time-preserving compilation.
Okay, yeah, thank you very much. Right, so I'm going to talk about, first let's start with some setup of if you have two programs written in different languages and you want them to talk to each other. You usually use an FFI for this purpose. And how this works is you interact with the languages at the source level using FFI that gives you a set of types, and you compile those down to your final executable format. And then at this binary format, you can link them together. And so usually how this works is that the FFI is almost always based on C types. And those compile down to a C-based ABI, application binary interface, at the target level. And so the advantage of using C types for the FFIs is that it's a widely supported, stable ABI, which is nice because it's widely supported so that you're pretty much guaranteed that any two languages will happen to understand C, and so they can use that as their common language. And it's good that it's stable because you need that for dynamic linking between packages that update independently. But C's type system is quite impoverished, and so this leads to some issues when you want to communicate between two languages that neither language is C, and they have rich type invariants as part of their type system. So for example, you want to share memory between OCaml and Rust. And so on the OCaml side, you have a reference, which is garbage collected. And on the Rust side, you have a box, which is uniquely owned. But the closest type in C for that is just a pointer. There is no really any difference between these two things. They're just objects in the heap. So you convert your OCaml reference to a C pointer through the FFI, and then you end up on the other side as not really anything in particular, just sort of this raw pointer in Rust that you have to remember came from OCaml and has certain obligations with the garbage collector, such as managing roots. And then vice versa, if you go from the Rust side, you have a uniquely owned box and you send it through the CFFI and you end up on the OCaml side with just some sort of raw pointer type that you have to remember to free. And this whole sort of region is just unsafe, unchecked, if you forget stuff, you end up with memory safety errors. And yeah, nothing in the compiler tool chain is preventing you from messing this up. So there's some prior work on improving the situation. So the prior work is a language called RichWasm, which was published in 2024. And the approach taken by RichWasm is that instead of just having one pointer type at the target level, you actually have two distinct pointer types corresponding to GC and manually managed references. And by keeping these distinct at the target level, it's not critical to safety that the source languages understand the other's memory management style, because the target language does understand it, and it will check that you're using the references correctly and that you aren't mixing them up. So as long as each individual source language has the ability to translate the types to the right target type, then the RichWasm type checker will ensure that it's handled correctly, it's memory safe. Now this is kind of interesting because now we have a single language with that supports two different memory management styles. So it actually has two different heaps. It has both a garbage selected heap and a manually managed heap. And because we want shared memory interrupt, those heaps actually interact with each other. They support cycles between them. And that has some interesting implications on what the runtime has to support. For example, the garbage collector has to understand how to free manually managed memory because it could own manually managed memory, and when it's time to collect, it might need to free some stuff there. And this is why, incidentally, why RichWasm does not use WasmGC, because it does not appear to provide a mechanism to make this interaction work well. So the story in RichWasm is that you have your two source languages and you compile them both to separate RichWasm modules. And then at the RichWasm level, there's a module system. You can import, export things from each module. And the benefit of using RichWasm, that now you have this stronger type system that gives you memory safety. It also makes the compilation slightly harder because you have to generate code that passes the type checker, but you get the benefits in exchange. And then when it's time to actually execute the code, you have to compile all of the RichWasm modules that you want to interop together as one giant compilation unit. And you compile this down to a final WebAssembly binary. But at this point, it's no longer possible to import or export or otherwise link with any other module. Or to be more specific, you lose the memory safety guarantees at this point. The result for RichWasm is that you get memory safety guarantees if you link at the RichWasm level, but once you've compiled, there are no more guarantees with linking with arbitrary WebAssembly code. But to sort of make this situation better, because it is desirable to be able to link with other WebAssembly modules, both from that were compiled separately from RichWasm or just came from some other compiler. What we want to do is define an ABI at the WebAssembly level. So first, quickly, what is an ABI? So the Swift language defines it as the runtime contract for using a particular API or for an entire library, including things like symbol names, calling conventions, and type layout information. And I think this is what most people think of when they think of an ABI, is its calling conventions and data layout. But we also prefer to think of it as in a slightly richer sense. We want to include information about memory ownership as part of the ABI, so that if you are not using a pointer correctly, that should be considered an ABI violation. And so how do we specify an ABI? So one approach is, this is the most common approach, is to just use pros So you describe the ABI in English as just part of the documentation, and a human has to interpret the specification and say, yes, this program is ABI compliant, or yes, this compiler produces ABI compliant code, and that's a subjective manual process. Another approach used by Wagner et al. Published in 2024 is called realistic realizability. And this is essentially a logical relation where it is indexed by source types, but it is inhabited by sets of target configurations. And by target configuration, I mean states of the target, like abstract machine, so like the code being executed, the stack, the heap, that sort of stuff. And because this is a logical mathematical object, you can now reason about it formally, and you can prove that a program is ABI compliant if you treat this definition as being itself an ABI. Right, and so how this works is that you have a source language with some source types, and you interpret your source types as these sets. And here the dot dot dots, like what counts as being part of the set, can use program logic, you can use a separation logic, you can reason about resources. And you can think of the interpretation of a source type tau as being the ABI for tau. But to really benefit from the safety guarantees that you get from having a strong resource-aware ABI is that you want to prove that your compiler from your source language to your target language actually emits code that is in the ABI. So to do that, you write a proof, and that can be quite a complicated proof. And also you have to reason about this separation logic, these separation logic things directly, which is a lot of compiler writers don't want to do that. So our idea to make this situation a bit easier for compiler authors is that we will insert rich WASM in the middle of this compiler pipeline. And we will define a realizability model for rich WASM types inhabited by WebAssembly terms. And we will also write a proof for our compiler that our compiler, if given a well-typed rich WASM input program, always produces WebAssembly code that adheres to the ABI. And actually, in order to do this, we had to completely redesign the rich WASM language to make it possible to define a realizability model for it in a reasonable way. So we call that rich WASM 2.0. And so what the source language compiler author has to do is write a type-preserving compiler to rich WASM. And as part of that compiler, they have a type translation. So they translate their source types into rich WASM types. And then you can just link these two things together, chain them together, and you get a WebAssembly ABI for a source type tau by just taking the type translation, the interpretation of the type translation of tau, where you provide the type translation, we provide the interpretation. And now this is a WebAssembly ABI, so now you can link with other WebAssembly modules. And if the other WebAssembly module was compiled from our rich WASM compiler, you get that the linking is safe for free. That comes from our proof. But if you're linking with some arbitrary WebAssembly module, you can still prove manually that it is safe to link if you want to. Right, so in terms of sort of compiler engineering effort involved on a large scale, the idea is that there is one compiler from rich WASM 2.0 to WebAssembly that we write. And then there are many type-preserving compilers from various source languages to rich WASM. And right down here, there's some complicated, gnarly proofs involving separation logic, semantic models, proofs written in Rock. And it's okay that this is hard because we do the hard work for you. We get this out of the way because we are researchers, we can deal with these complicated things, and then the compiler engineers just are up here writing their type-serving compilers and picking and choosing types from the Virtualism 2.0's, from the type vocabulary of Virtualism 2.0 in order to encode their ABI choices. So just to quickly go over some details of Virtualism, it supports polymorphism for functions. And as part of the polymorphic quantifier, there is a kind constraint on types. And this kind includes representation or size, depending on if it's a WebAssembly value type or a heap type, type in memory. And it also includes some details on like resource management, whether you can copy or drop something. This is inspired by the kinds or calling conventions paper. And right, so this sort of kind system was necessary to facilitate an ABI because we need to, we don't want to monomorphize because that would sort of mess up the ABI. So we have these monomorphism restrictions where you can use polymorphism over types, but you must be monomorphic in the representation. And the nice thing about this polymorphic setup is that you can now encode things like ML has a uniform representation. All of its types are boxed by default. And you can encode this by saying that, well, all of my polymorphic functions quantify over types that are in my uniform representation, which is a pointer representation. That's expressible in the kind system. Yeah, and for our model, we use Iris, and specifically Iris WASM. And just to give a flavor of some things in the model, a manually managed reference, this is a rich WASM type, is interpreted as unique ownership of sort of a virtual heap points to. And a GC reference is that same points to, but now it's in an Iris invariant, which allows sharing and sort of aliasing of the pointer. But these are abstract locations. These are part of like a logical heap. And where the actual ownership comes from is in the interpretation of the pointer representation. And this uses pointer tagging to distinguish, like, is it just an integer, first of all, or is it a heap pointer, in which case, which heap is it in? Because we have two heaps. And the sort of separation between virtual and physical allows the runtime to manage the lifetime, such as when the garbage collector has to collect manually managed memory. Things are in progress. So this is work in progress. The big thing that's still in progress is the proof of compiler API compliance. So we are proving that if you give us a well-typed virtualism program and we compile it to WebAssembly, then that is in the model. That proof is very non-trivial and is sort of we're improving the ergonomics of Iris WASM, let's say, as we prove it in order to make the proof a bit easier to do. And we also have a case study involving two source languages. One of them is a core ML, which is reflecting the garbage collected side of things. And one is a linear lambda calculus reflecting the manually managed linear ownership side of things. These compilers are type preserving, but we don't prove that they're type preserving. They're just unverified compilers. But we're working on examples. And yeah, so to conclude, we're developing Virtualism 2.0 to make it easier to specify a memory-safe ABI for your language. There's two parts to it, and we do the hard parts, is our pitch. And that's it.
So we have time for some questions. Could the next speaker prepare himself or herself at the time that we do the questions? Are there any questions?
Do you want to connect?
Yes.
You said that you had to redesign Virtualism to make this work. Could you elaborate a bit of what the problems were with the original version?
Yeah, so the main issue was polymorphism. So the original rich WASM 1.0 had to monomorphize all of its polymorphic functions as part of compiling to WebAssembly because it had like a very expressive form of polymorphism. So what we had to do was add these monomorphism restrictions with the kind system to make the code generation more tractable without monomorphization. That was the main change.
Thanks.
Any other question? I think we can thank the speaker again. So the next speaker is towards formally secure compilation of verified F-star programs.
Yeah. Thank you. Can you hear me? Yeah. Okay. So hi, my name is Cesar, and today I will talk about how to compile verified F-star code to an ML language in such a way that the compilation is verified and is end-to-end. And this is joint work with some people, with amazing people, and some of them are here, like Catalina and Abigail in the room, and Theo will join later in the week. Can you hear? Can you hear me? Does it work well? Do you want to move it? Yeah, okay. Okay. I'll keep it here. Okay. Yeah, so let's start with what F-star is. So F-star is a proof-oriented language in which one can write programs. Like if you want to verify a web server, you can write the web server in F-star. We can write a specification, and this specification is written by annotating the code with refinement types and pre- and post conditions. And F-star will check that the web server satisfies the specifications, and if the check is successful, then we have a mathematical strong guarantee that this is the case. And as I said, F-star is kind of designed to be used as a programming language. One should write code in F-star and then extract it to other languages such as OCaml. And this code can be run by itself or can be linked into bigger code bases. And actually, there is a big case, a big example, a successful use of F-star is the Evercrypt cryptographic provider that is verified in F-star and then is extracted to C and other languages. And this is integrated in Mozilla Firefox, the Linux kernel, and the WireGuard VPN. So this is, yeah, how F-star was used successfully. Only that there is a problem with this idea of extracting code from F-star. First, the extraction, the compilation is trusted, but then also the linking with the unverified code is trusted. And this is problematic because if the code is buggy or malicious, like the unverified code is buggy or malicious, it can break the internal logical invariance of the verified code. And this will lead to unsoundness and probably security vulnerabilities. So we basically lose the strong guarantees we got by verifying the code. So what we are trying to do is to propose a compiler that is goes from F-star to ML language, and that we are able to verify end-to-end, and we are able to prove a security proof about it. And we want to do this fully in F-star. And we start by looking at terminating higher order I/O programs. So by I/O programs, we mean that they can interact with the environment, but they don't have any internal state. And by higher order, we mean that the verified and the unverified code can pass between them callbacks. And this is actually work that comes after previous work. So this is work we published 2 years ago, like verified. 2 years ago we published a verified secure compilation framework for verified I/O programs, and in that work, what we do is that we take refinements and pre and post conditions and we convert them into dynamic checks so that we guarantee that by linking with unverified code, it's secure, right? So we have their end-to-end proof and the proof of security. But that work is missing exactly this piece at the bottom, extraction from F star to mainstream language like OCaml. And this work is addressing that. So we only have to do this bottom part and start from kind of code that doesn't really have refinements and pre and post conditions at the boundary between verified and unverified code. So why is this step so challenging? So let's take an example. We take this program that takes as an argument a library that will be unverified. And this program is returning an unit and it's in the I/O monad. And this program is really simple. It reads a message, passes the message to the library. It writes the result of the library. And the way we are going to verify this is by using a trace producing semantics where for each I/O operation, we associate an I/O event, right? So for read, we associate an event. For the library, we don't know what it is going to do, so that will be a gap there. And then for the write, there will be another event. And basically what we want to do is take this program that's written in F star and compile it to something that looks like this. That's purely syntactic. That is just a syntactic expression. So what's the problem? Well, the problem is that this all happens in F star, and the top program is a shallow embedding. And basically we want to get out in F star a deep embedding. And there is no way to do this without some kind of meta program being involved. And this is kind of tricky because if, for example, if compilation uses quotation, which will be a primitive, right? And its quotation will be a meta program, then we have to verify this quotation, and then this will involve meta theory of F star, and which it lacks, formalized meta theory of F star, which it lacks, and all of that to have an end-to-end proof. So this is kind of problematic, and yeah, we kind of, I mean, this is why this is complicated. And after reading related work on relational compilation and synthesis from KKML, we came up with a different technique to solve this problem. And we propose our version we call relational quotation that involves two parts, a typing relation and a meta program. The typing relation is kind of special, and it will define the subset of F star we want to compile. And if you look at the type, it's pretty standard. It takes a typing environment, a type, and expression. The difference is that the type is not a syntactic type, it's a F star type. And then for the value, it's not a syntactic expression, but it's a F star value, which is kind of weird because this is already typed as A. But we'll see in a second how this works. And the fact that we use here F star values, like F star values are closed, right? There is no notion of open, closed F star values. We open them up by using this, like environment passing, right? So here we pass an evaluation environment to this value to kind of mimic opening it. Right, so after we have this type, like the type of the typing relation, we can define its rules, and they are pretty basic. So for false, right, we have false is typed bool, and for yeah, and these are again F star bool and F star false. For variables, it's pretty, it's again pretty standard. We only hear that because we have this evaluation environment and it works like a stack, we take the top of it. And then for lambdas, we have the if we have a body that's typed as B in a typing environment where we have an A, then we can type the arrow right to A to B, And you see that we take this, the argument of the lambda, and we put it on the evaluation environment. So this is kind of, it's a bit weird, but it follows the standard typing rules. And actually, to support the IO monad, we define two mutually recursive relations following the typing rules of fine-grained call by value, which was pretty interesting to us to find out. So how do we use this? So basically here it's manually writing the typing derivation for the program that I showed earlier. And so basically we only have to write the constructors, and we don't have to define the some of the types. And basically here, this derivation is going to build a new program that will get unified with the program we want to type. And if f star is able to type check this, it means that it's the derivation of the program we want. And what's important about this derivation is that it captures the program's quotation. Like if we look at this derivation, we kind of can see the syntax of the program. So this is why this is so useful, because now we can see this. So how are we using relational quotation? So instead of using the meta program to do compilation, we use the meta program to find this typing derivation of the program, and this will be in our source language. And then, so basically our source language asks for a program and its derivation, and then it can build its syntax. And this is just projecting out the syntax from this typing derivation. To say a bit about the meta program at some point we are still working on this, but at some point we were able to use just type class resolution to find these derivations. So it should be pretty simple. Okay, so the important ingredients, like what's important about this model is that it allows us to do an end-to-end proof by using the typing derivation and by using the typing derivation. So what are we proving about this, our compiler? We prove robust relational hyperproperty preservation. This is the strongest criterion of Abate et al., which is stronger than full abstraction. And this guarantees that compilation preserves observational equivalence. So this is what full abstractions gives one. Non-interference and trace properties. And we prove this by using a cross-language logical relation. And that relates a shallowly embedded program to a deeply embedded program. So it's kind of asymmetric. And the proof, again, is done recursively on the typing derivation. And what's the most important is that we did not have to do any meta theory of F star. We just have to define this typing relation and do the proofs losing the logical relation. So we are, so to recapitulate, we propose, we are working towards a secure compilation that is end-to-end verified, and we prove strong security criterion about it. And all of this is fully mechanized in F star. And the key idea was to kind of, instead of using metaprogramming to compile, was it to kind of, in the source language, to find this derivation. That was it. Thank you.
So, any questions? No? So I have a question about your meta kind of task. You said that it's quite easy to implement the meta program, taking you from this shallow embedding to the deep embedding. Did you have to modify in any way F star in order to do that, or it's just?
So this is a meta program, right? So we don't. Like, not yet. For now, we did not find any reason to modify F star.
Okay.
F star already has, there is meta F star that offers tactics. so it already has great support for metaprogramming.
But when we're doing the questions, can the next speaker to set up his machine or a machine? Yeah. Ah, okay. And I mean, you still have to establish some kind of proofs in order to relate both. Were they fully automated?
So the relation between the derivation and the program comes from the dependent type of the typing relation that says that this is the derivation of the program.
Oh, okay. So it's this typing mechanism that.
Yes.
Okay. Thank you.
So the title says terminating. What would it take to cover non-terminating programs? You mentioned the web server at the beginning, which is typically a non-terminating program.
Yep. So right now we are looking at how to compile Shaolin embedded code, and so basically one will have to kind of pick a monad to do non-termination. So right now the standard is to use I-trees, but I-trees are not supported in F-star, and this is why kind of we didn't look much into that. And yeah.
No other question? So let's thank the speaker again.
We have
yes. And the next speaker is Jeremy Thibault from EPFL.
Okay, hi. So thank you for being here. I'm Jeremy. So this is work done with Basile and Catherine when we were at MPISP. And today I'm going to talk about proof techniques that we've devised to help us verify low-level secure compiler backends. And this proof technique, we call it blame-aware recomposition. So I want to start with a bit of background and context. So right now, many systems are still written in unsafe languages like C. And it has some issues. C has many undefined behaviors, buffer overflows, use after free, double free, all those. And they can lead to devastating attacks. For instance, Microsoft and Chrome report that 70% of the high severity bug that they encounter are memory safety vulnerabilities. And unfortunately, it's not really realistic to replace all that unsafe code by nice safe code. So instead, something that has been proposed often is mitigations, and one of it is compartmentalization. With compartmentalization, we start by splitting our source code in different compartments that are protected to from each other and interact through protected interfaces. This code that is compartmentalized gets compiled to machine code that is still compartmentalized, that might be linked with some external context, low-level libraries, for instance, that might already be compartmentalized. And then there is a compartmentalization mechanism that protects all of this. Hopefully, this compartmentalization mechanism is strong enough to preserve security properties of the source, and that's what I would call a secure compilation chain. So in the past, we've done some work on formally verifying secure compilers that use compartmentalization, and we prove a theorem that basically states that low-level finite executions can be explained in terms of the source. And that corresponds to the preservation of safety properties. So just to make it a bit more concrete, if at the bottom you take this entire program and it produces a finite trace M that records calls and returns and their arguments, then through a process called back translation, the theorem states that we can use a back context, a source equivalent of the low-level library, and that we can link it with the source code and produce the same trace. So we've built some compilers and we've verified that they satisfy something like this, except we didn't. So actually, what we did is we stopped the verification just before reaching that very low level. And instead, we have verified something at an intermediate level, which has still intermediate code that is compartmentalized. It still has a context that is compartmentalized, except it's not as concrete as a real backend. For instance, this intermediate level uses a block-based memory model, while in the concrete backend, we would prefer to have a flat memory model, which is closer to reality. In this model, the code is separated from data, while in practice, code actually lives kind of in the same memory space, and there are protection mechanisms to isolate it. And what this means is that in the intermediate language that we considered, we only had an abstract compartmentalization mechanism that was built in the semantics and was acting more as a specification of the actual behavior of a concrete implementation. Instead, we would want to actually verify that concrete implementation of the compartmentalization mechanism. So you might ask, why did we stop here? Well, we stopped because the proof technique that we were using was not really working for us at a lower level. So I will now explain a bit this proof technique. So basically, the idea was at this intermediate level, we were starting from a compiled program, P down arrow, linked with a low-level context, that produces some trace. And as I say, we need to prove that there is a source context that we will call CS that can be linked with P and produce the same trace. So what we did is actually do a back translation to get a CS, but also a new program P prime that produces the same trace. And that's not the result we want, because we want, instead of P prime, we want P. We would use compiler correctness here to go down to the intermediate level by compiling this CS P prime. And then we would have a step called recomposition that takes the P compiled from the left and the CS compiled from the middle, put them together. And then we see that everything is compiled, and we were able to go back using compiler correctness to the source. The reason we're using a proof technique a bit involved like this is that it really allowed us to reuse existing compiler correctness results instead of having to redo them from scratch. Unfortunately, recomposition that we use here at the intermediate level is the source of the issue, and we cannot use right away at a lower level. So why is that? For this, I will even explain a bit how we proved recomposition. So again, we start from two executions of different programs, but that share the same trace, and we obtain a recomposed execution. Concretely, we start from, we split our programs in an A part and a B part, for instance, and we start from A1 and B1 on one side, A2 and B2 on the other, and we want to take A1, link it with B2, and show that they do the same trace. So if A1 and B1 and A2, B2 linked together produce the same trace, we want to obtain A1 from the top, linked with B2 from the bottom, and show that they generate the same trace. We're using a very simple, conceptually simple so we're saying, imagine, for instance, we're starting with in the A, that if A starts with a silent step in the top execution, well, in the middle, we are also starting in A1, and we were proving that we can do the same silent step. And we were proving that we could repeat this until we reach an event. In the first execution, a call from the A part to the B part. And then we are saying, well, because the two executions produce the same trace, we can reach a point where we're going to do the same call in the bottom execution. And that means we can prove that A1, B2 performs the same call. And this time, because we're calling B, we go to B, and we repeat the same argument with silent steps in B this time. So we do the same again. And then we encounter a return. Same reasoning. There is a return at the top. And so there is a return in the middle, etc., until we produce the entire trace again. So this is nice, but this doesn't actually work in a concrete level. And for instance, this is because of these silent steps. So here, when the A1 part steps, it cannot actually know about whether it's linked against B1 or B2. Otherwise, there would be ways for it to make a different choice. And so do different things, and we could not reproduce the same silent step. Said another way, it means that cross-compartment observations must be recorded on the trace. And that's really not possible if we only record calls and returns at the lower level. So for instance, because we have a flat memory space, compartments are able to observe the allocation pattern of other compartments. So they know how many allocations the other compartments have done, and they can do different things based on that. Similarly, all code is usually laid out sequentially, and so it's quite easy to observe the size of the code of other compartments. Finally, there's no distinction between code and data. So code can even be read directly if you want, without any additional protection. But the thing is, these are not really about safety properties, which are the criterion we care about. Those are about code confidentiality. And so we thought there should be a way to make the proof work. Our contribution is to indeed extend recomposition to this lower level. And the key idea is that we can characterize these behaviors as these behaviors that observe things about other compartments as undefined behaviors with respect to an overlay semantics, which is represented by this funny arrow here. So the overlay semantics we introduce is just the same as the low-level semantics, but it prevents all these recomposition breaking behaviors, such as reading the size of the code, reading code directly. And what we mean by undefined behaviors with respect to this semantics is that it's behaviors that are allowed in the low-level semantics, but not in the overlay semantics. The second insight is that recomposition manipulates 3 compile programs and 1 low-level program that we will discard. And so maybe it's not too bad if that low-level program does undefined behaviors. So this looks in the end a bit like this, except that here we have 2 different semantics for the low-level syntax, and one is more restrictive than the other. The overlay semantics is much more restrictive. So blame-aware recomposition that we introduce looks very similar to the previous recomposition, except that when we manipulate only compile programs, we are reasoning in the overlay semantics. On the other end, when we're manipulating a non-compile program, we're reasoning with the low-level semantics, but we add one more condition. Either that this execution has no undefined behavior, meaning we could actually reason everything in the overlay semantics, and in that case, it reduces to the previous recomposition proof, or that the undefined behaviors happen only in the context part. So when you have this property, you can actually retrace the steps of the original proof steps, this time between the overlay semantics and the low-level semantics. And you can prove again the same criterion, and then by vertical composition, you can get it for the entire compilation chain. However, before I talk a bit more, just some limitations of this approach. Precisely characterizing all the behaviors that break recomposition is hard, so we are not able to do it. For instance, take this piece of code, it allocates, it calls another compartment, it allocates again, and then it does different things depending on how many things the intermediate compartment has allocated. Well, this is very hard to find to track in the overlay semantics. We would need very fine tracking of pointers, and so we decided to not do it. Instead, we use additional lightweight protections in our concrete implementation of the protection mechanism by using a custom allocator that separates memory spaces to hide the data layout of each compartment. That's not strictly necessary to obtain the top-level theorem, we think, but that makes the proof work much better. So we apply this technique to an existing micro-PriSC backend that was only previously tested. So it's a programmable tagged architecture where tags are used to enforce compartmentalization. And we only needed to do very slight modifications related to the memory layout. Our proof technique, to prove blame-aware recomposition, we have a three-way simulation that is very similar to the one we are using for recomposition. So we have proven the main lemmas for this recomposition. Not everything is finished. This is still ongoing work. But what's important is that when we actually prove these main lemmas, we have to reason about tags. We have to reason about the compartmentalization mechanism we just implemented. So that gives confidence that we implemented this micro-PriSC correctly. So we're missing still a few things. Some results on big vectors. We have some performance issues with ROC. And and some results to tie everything together. So just to conclude, we're working towards a verified low-level backend for a secure compiler for a compartmentalized language. This has a flat memory model. Code is readable. You can even execute data if you want in that language, in that low-level backend. For this, we use blame-aware recomposition, a novel proof technique that uses overlay semantics to characterize some behaviors and undefine. And we still need some additional protections, unfortunately, to make the proof doable. So some questions we'd like to explore. Can we get rid of these unnecessary protections for the criterion we care about? Or on the other hand, can we generalize to a much stronger security criteria since we have additional protections? So I think that's all for my talk, and I'd be happy to answer any questions.
No questions? No? So, okay.
I wanted to ask about your overlay semantics. Does it change the events on the trace, or is it the same trace for all levels?
It is really the same trace, and this is very useful because that means we can reuse things like the back translation to go back to from a low-level execution. We're using the back translation to get something in the overlay semantics by back-translating and then recompiling down.
So I too have a question. But you at some point you had a slide with the problem of information leakage through malloc, and essentially with too strict semantics, this would have prevented using any malloc. And you use this separate allocation scheme. There was another method used in variants of ComCert to give low-level flat semantics to things, by people like Pierre, for instance, which was to say that behavior is defined. Basically, if it defines the same behavior in all possible concrete memory allocation layouts. Have you considered doing that?
Well, I believe if we were to do that, we would exclude a lot of programs that we would want to consider in our program. So I would assume that many low-level contexts would not have defined behaviors with this kind of semantics.
Okay. No other question? So we can thank the speaker again.
I don't know. Yes? All right. And can I stand from this other side? Everything okay? Can I start? Okay, so hi everybody, I'm Carmine from the Barkhausen Institute of Dresden. Today we talk about our ongoing work on building compilers that preserves all the properties that you can prove in a weakest precondition calculus for your source language. But I have to put this one. Yes. Does it work? No. Okay, then I will just stand next to the laptop. Okay. A second. All right. Okay, but let's start by giving you a bit of the context in which we are working. So at the Barkhausen Institute, we are developing a framework for the verification of Rust programs. And if you're curious, you can take a look at our paper at PLOS last year. The framework works as follows. You write your program in Rust, you implement your program in Rust, and this gets transpiled into ROC. You can give a specification for your program, and you can prove this specification in the weakest precondition calculus we implemented in Iris for our language. This is a very small example, but on the long run, we plan to formally verify the whole unikernel. There is a project called Formula 5 in case you are interested. Of course, we don't want just to verify our Rust programs. We also want to compile and execute them. And we are interested mainly in two targets. One is an extension of RISC-V with compartments. Another one is a cloud architecture. Of course, since we spent a lot of effort in building a program logic and verify source program, we would like to preserve the specification that we proved in our calculus. And the question is, of course, how we plan to do it. So we are relying on interaction trees that I will briefly try to recall in one slide. So interaction trees or I trees are a general purpose data structure that you can use to represent the behavior of effectful and possibly non-terminating computations. I like to visualize them as infinite trees, and on the nodes of these trees you can find either an event like read or write, or you can have some other kind of nodes that represent internal computation that don't have any externally observable event. There are these silent steps. And you can have terminating nodes like leaves that instead represent a terminating computation that returns a value, so like this, return R. I will not recall all the nice properties of I trees, but I would like to notice that the I tree that you see in the slides at the moment doesn't have any particular meaning, because read and write are just symbols so far. But we can, of course, give it a computational meaning by interpreting these events in a monad, for example. And you can interpret read and write in a state monad, and now the I tree on the slide will represent a stateful computation. For the purpose of this work, we are not only interested in the computational meaning, giving a computational meaning to I trees, but we are interested in assigning it a logical meaning, because we want to talk about the weakest precondition calculus. And we are using a recent work from POPL last year, program logic a la carte, where the idea is basically you just need to specify pre and post condition for the triggering of an event. So for example, here maybe I simplified a bit. To trigger a write event, you need ownership as precondition, ownership of the location to which the variable y is pointing to, and you will return as post condition this ownership with the updated value. So once you specify this pre and post condition for each of the events you can trigger, then you can easily get a weakest precondition calculus for your programming language, given that you gave an I3 semantics for it. And quite interestingly, and also I would say a result that we all expect, is that if two programs are denoted with I3s that are bisimilar, then the properties that you can prove for one program also hold for the other programs, of course, in this weakest precondition calculus. And at this point, as you might have guessed, we want to use these as proof technique to show that our compiler preserve the weakest precondition calculus, the weakest preconditions that we proved in our calculus. Of course, you just need to show that source and compile programs are denoted with bisimilar I3s. So to put everything in one single picture, we are defining, we are giving a formal semantics with I3 to our source language. And from that, we are deriving a program logic in the form of a weakest precondition calculus. We are doing the same for the target language. And then to verify that our compiler preserves the specification proved in the source, we will show that source and compile program are denoted with bisimilar I3s. Of course, this is a nice story, but it's very high level. There are several challenges that we are facing and that we still have to solve. But let me get to them with some order by telling what we so far think to understand, at least. So first of all, we know that we can design program logics in a kind of very modular fashion once we have a I3 semantics. No? You just have to specify this pre and post condition for each event. And if you want to add a new effect to your language, you just have to add the, just have to specify the pre and post condition for the new effect, right? And there have been very large projects like POPL'26 and more recently Jasmine that gave a formal semantics to realistic languages. And in these two projects, people certified compilation steps by showing bisimulation of I3s, so adopting the proof technique that we're also considering. There are, however, they are facing, of course, our same challenges that are mostly related to the fact that values of the two of source and target languages, and of course each intermediate language, can be different. Memory representations, memory layout can be different. Effect events can be different. And so in the LLVM project, I understood that they face these problems by a so-called layered interpretation approach. So they reinterpret source and target I3s into a common layer where they can show a bisimulation. Of course, this would be not really the best for us because we would preserve the weakest precondition only up to this common layer while we want to go all the way down. More recently in the Jasmine project, people introduced, the authors introduced more liberal notion of bisimulation that allows you to relate I3s that are also structurally different. In particular, they can relate an I3 that terminates with an undefined behavior with an arbitrary continuation. That is actually exactly what you want to do in compiler verification. We will probably follow a bit this path, but in this case, the challenge is that you need a more precise description of what's the property that holds after compilation. We plan to reuse some previous work from the past, but still the full details have still to be worked out, and here we are dealing with a resource-aware logic, so there are some non-trivial differences. And in our PriSC submission, we describe these challenges in a much simpler setting rather than Rust. We consider a toy imperative language that I guess you are all familiar with, IMP. And as target, we consider a toy assembly language. This is the same of the original I3 paper. And instead on the right, we are using a communicating sequential processes. That is a process calculus language by Tony Hoare. So you can take a look at the PriSC abstract and you will find a link to our GitHub repo, but we are not planning to push on the repo nor to maintain it. It's just to describe the challenges and the idea. And with this, I'm happy to take any suggestion, questions. Yes, it was fast.
So you took only 10 minutes
yeah,
instead of 15. So
I want to take questions.
We have actually time for questions, and we will not even be late for lunch. So.
Thank you. I have one maybe surface level understanding question.
Yeah.
You mentioned that you're not interested in interpreting the effects into actual monads and you just want to specify them. One thing I'm curious about is that when specifying semantics with I-trees, it's often, non-trivial to find out the order in which we interpret the effects because the monads don't stack, the monad transformers don't commute. So there's interactions between the effects that are non-trivial. But you mentioned that in your case, you can just add new specifications for new effects if you want to add them. So does that allow you to bypass the difficulty of interference between the effects? Or?
I would say yes, but we are basically just user of this program logics a la carte. So maybe this is a question for the authors of that work. Yeah, in this framework, you just need to specify the pre and post condition for each effect and show an adequacy theorem. So this is maybe what you're talking about. So you have to show that somehow there is an adequacy with the previous existing effect.
All right, that
okay?
might be it.
So very nice. That can be an interesting proof.
Right, thank you.
Any other question? No? So actually, I have a question. So they are, interaction trees are one among several formalisms that more or less try to express this kind of notions. Have you tried some alternatives? What are the pros and the cons?
Sure. Yeah. So this is something. Maybe this is the only question for which I don't have a backup slide, but I've been thinking about it. Of course, like the more natural would be probably using some trace-based approach. But for that, so what would become, let's try to think of what to do there. You need a trace semantics for your programming language. Then you need to build your program logic by looking at that trace semantics, right? And then you need to show some preservation of this. So it's something that is in this I3 framework is given by one single framework. Is in particular getting this program logic seems to be not too complicated. While with a trace-based semantics, you should do a lot of work to instantiate iris from a small step operational semantics. At least this is my take. Plus, of course, maybe the advantage would be that you would reuse some trace-based criterion, trace-based proof technique to verify your compiler. But still, then you will have to find a connection between the traces of the target and the properties that hold in the target.
And you don't have any problem with termination because you're doing weakest precondition, not weakest liberal precondition. No issues with termination.
So I believe this is the calculus that you get here is partial.
Partial correctness.
Yeah, partial correctness.
Okay. So I think we can take this.
Hi, thank you for the talk. So are you gonna build your own Rust compiler, or are you gonna be like the existing one?
I see people smiling in the audience. No, we are going to build our own. At the moment, we have some pieces, the very hard, like the upper part of the compilation chain, almost implemented from, let's say, how much familiar are you with the compilation chain of? Okay, so there is the first intermediate language is called typed high-level intermediate representation. The second one is called a MIR. So we are, I don't know, MIR medium, I don't know. We are implementing, of course, first from tier to MIR. Okay. And we will try to apply this technique there. And then we will, at some point, we might resume to some existing compiler just to have a first working compilation chain. But yeah, the idea is to go all the way down at some point.
all the way down, would you take also existing formal semantics for the target, like RISC-V? I'm thinking about Salle, for
Yes.
instance. Yeah, that would be super cool.
That would be super cool. We agree. The only and this is also what we would hope. The missing brick, I would say, is that Salle doesn't come with I3s. Yeah. So we would have to adapt, or I mean, we are still keeping on the table the fact that we can compare with some trace-based approach. So Salle, I believe, maybe you can get some traces more easily than I3s. So we'll see. We are still at early stages of this compiler.
No other question? So I think we can take the speaker again. Ah, no, there's yet another one? Okay.
Yeah.
This thing is in offline.
Sorry?
Okay. So maybe I missed something, but the bisimulation is necessarily needed in your proof chain, because in many cases we just prove one side of simulations and for compiler correctness. So
for this I have a backup slide. Not really fitting completely your question. So there is something that I was not really explicit. This rule that I mentioned that says that if two I3s are bisimilar, then the WBs are the same. So this is a homogeneous bisimulation, so very strong. But it's still useful. It's still useful when you can embed the source events into the target. And if you look at our PriSC submission, you will find, well, first of all, a program optimization input to imp, but also a imp to CSP, that more or less CSP embed imp, in which we can use this lemma, this rule here. You need it. We are also open to explore one-way simulation. The point is that there is a lot of technical work to define these simulations and bisimulations in over I3s. There is a lot of work to be done in ROC. Show trivial stuff like preservation through bind and return, respect all the monadic stories and interpreter and whatever. If you are familiar a bit with I3s, you might know what I'm talking about. So we are trying to reuse as much as possible what's there and try to implement the least possible extension.
Yeah, thank you for answer.
But yeah, I would say, in principle, we are interested only in one implication here. And also for me, it's very natural to just require one-way simulation.
So you can really thank
Thank you.
So maybe I should mention for the people who are coming in now, we had a unexpected last-minute change of schedule because the first speaker had to go to the hospital, and we are doing now the talk that got delayed from the morning. And then continuing with the session on side channel security.
If there would be anyone who would be so kind to just quickly run out and find that he can downstairs, that would be really nice.
Because he's waiting. He wanted to like see this talk.
It's also recorded.
Sure.
I don't know if people know him.
Was just like if someone would be willing to, that would be nice. Yeah, we just switch.
Okay, it says 2 o'clock. Welcome to the timing side channels session. Only one announcement again, that the first talk is postponed at least. And we do the talk that we postponed this morning by Stefan, and then we return to the usual schedule of the timing side channels session.
There's a little bit of timing channel possibility in here, so I think it can kind of fit. This is probably not too much of a interesting statement or surprising statement for most of you in here, but module systems, they're hard. And if it's a distributed system, probably just doubly so. For example, think we have Alice who wants to send a message to Bob. So she sends a function f, which depends maybe on some module on her machine too, to Bob. Bob doesn't know it, so Bob might then just ask Alice, can I please also get this module, because otherwise I cannot run your code. And Alice obliges, sends Bob the code. But hopefully then Bob would actually has cached somehow this module, so when Alice later is going to send a different function g to Bob, then Bob doesn't actually have to ask a second time. So if we, instead of having everything being sent by value, we might want to have function closures being referencing different things based on like a hash instead. And based on that, we can maybe then improve the network traffic and make things run faster that way. And actually, it's not just modules, it's any kind of dependency that you might have in this kind of a function closure. Thank you. Charlie is now going to be somehow branching on some secret, and if so, that Mallory wasn't actually supposed to. So you will still need to like remember to also downgrade the things you're going to be caching. Finally, for availability, currently in the distributed systems we're going to be looking at, everything is being sent by value, and that has a nice property. That so if Alice is going to be sending this function f to Bob, and then kills her machine, and Bob then also forwards again to Charlie, and then kills his machine, and Charlie forwards further on, killing the machine, and so on, until we get to Zoe, who is then at the end actually wants to execute this function. If we're adding this caching in, or we're beginning to add some like references to modules and stuff in, we could run into an availability issue, as in, how can I actually execute this function when the origin actually isn't available anymore? So that is still something that we want to be preserving. And all in all, the question we were asking previously then actually boils down to how can we add an information flow aware cache inside of a distributed system. In particular, though, for our case study here, we are looking at the Troop programming language from Aarhus University by Aslan Askarov and others, which kind of looks like this, an SML programming-like thing with additions inspired by Erlang and a few other places. So this gives you ability to actually do decentralized programming, so distributed systems that are truly open, you can join with any code you kind of want. And it organizes by itself. It also then includes information flow control to actually provide read and write permissions on the types of every value. And whether these read and write permissions are actually violated is then ensured by a monitor at runtime. It's a monitor because the programming language by itself is also made dynamically typed, because otherwise it would be difficult to have a system that can actually be truly updated with new code, with new types that you've never seen before, and have systems interacting where they don't actually know the code of the others. So when we're looking at this question, what we are actually trying to think about is, can we do this with the minimal extension to the trusted computing base? Because hash maps or caching is just difficult. That is, there's thousands of examples of that being the case. And in this case, if we don't want to extend the trusted computing base, we need to implement it in some other way. But we already have a programming language that does deal with information flow. So maybe can we do this by actually using Troop itself in this use case? Based on at least our first prototype here, if we look back in the first example with Alice sending something to Bob, we have now implemented a cache inside of Troop itself, which is then running as a separate thread, run by the trusted computing base. So when Alice wants to send a message, the trusted computing base is going to send that message to Bob with some dependencies only referenced by hash rather than actually sent by a value. At the same time, Alice is also going to be sending a set message to her own cache thread, which is then going to be storing this value down, storing this value. Bob is then going to be looking at his own cache thread, whether there's actually something stored here, which then also is going to give you something back. Maybe there isn't anything cached, or there is something cached. If something is cached, we're done, and we got the nice performance increase that we wanted. Otherwise, the trusted computing base can then send a miss message back to Alice, and Alice will then look up in her own cache and find the value for Bob. And in which case, Bob can then actually fully deserialize the message and run the code given. And remember also this for later, such that for another time around, when this dependency is missing at a different time, Bob can just insert it himself. This thread, the code actually needed for making this cache thread in Troop was actually very, very tiny. So we needed like a few lines of code to like take the SHA string and turn it into like a 32-bit integer. We needed only like 20 lines of code for actually defining the thread that manages the hash map, the cache, where we then have implemented a hash map inside of Troop, which we can get back to that, but we need to probably recreate or redo that one from scratch, but that's a different thing. But in terms of like the interface, it's just purely like inserting with into the map, the authority, and then the key value pair. So the interface is very similar to the other usual things you would have in a programming language like this. And then we need a little bit of a public interface for the trusted computing base entry points, so the setter and the getter, which are going to be dealing with sending the messages. And finally, there's, because we're in the timing part now, there's a little bit of a wrapper for the sandbox feature of TrueBridge to also try and see if we can mitigate some timing attacks. The hash map itself, based on the current prototype, what we have come up with at least is a little bit of a specification for how you would like to have this hash map work. So if we think back to like the previous, one of the previous examples we had, Charlie is forwarding some function f to Bob with some dependency on some module. And this is secret at Charlie's level. And here Bob might say, I don't know this, I'll give a miss on that. If Alice later is going to also have a same dependency sent to Bob, Alice should also be given a miss, because otherwise she would know that Charlie had sent that message. But Alice is sending it at the public level, so when Dorothy is going to be sending a message to Bob, even if it's secret at Dorothy's level, this is okay to actually be a hit, because it's fair enough that there's going to be information flowing from Alice's public message to Dorothy in this case. So in terms of like how the hash map should be designed, it should be like a single data structure with public, where you can put in public and secret key value pairs. And then it can provide information flow aware projections of the entire insertion operations history. So you have some history here. You insert x is equals to 1 publicly. You then insert x equals to 2 at Alice's level. And then y equals to 3, and removing x again at Bob's level, and finally inserting y is equals to 4 at the public level. If you want to project this to the public level, you will just get the insertions at either end. If you're going to be seeing go for Alice's projection, then you would actually see this override of x is equals to 2. And finally, if you go for Bob's level, we will see x is equals to, x has been removed, but also y still equals to 4, because this insertion is newer than the previous insertion. And following a specification like this would give us essentially one data structure that gives us this behavior that we want. Is as far as we can see. Any questions on this? Maybe my example didn't work out. I see a few confused faces. Okay, we can take that later maybe. In terms of what actually we have identified needs to be part of the trusted computing base, the miss and misreply messages you saw earlier, where you were like, I don't know this, can you please send it to me? That has to be sent by value, so that shouldn't be using the dependency system as part of the resolving the dependency system. So that might need to be part of the trusted computing base. Also, it seems to us right now that we would want to have extracting or inserting the dependency should be done as part of serialization and deserialization. And that requires introspection of functions and their closures, which isn't something, reflection might not be something you want to have as a language feature. So in that case, you want to have it as part of your trusted computing base. And similarly, hashing some values would also have to be in the CCB, because if you're hashing a function, you need to hash the source of that function, or the bytecode or something like that. And finally, also, the scheduler or the interpreter in that case, whatever is running the code at the end, also needs to have a little bit of refactoring, maybe, such that you can actually run code from a TCP context. Until now, at least, in this case of Troop, at least, the problem has been that you could only run Troop code from Troop code, but now you also need to run Troop code and wait for the result of Troop code from the trusted computer base itself. So all in all, we had this question: how can we actually add an information flow aware cache? And we hope at least the answer is, based on our prototype, based on everything you've seen, the answer can be that you can actually do it by bootstrapping the information flow aware runtime. Thank you.
So we have time for questions.
So I understand the kind of partial views that you give to different users, but how do you avoid timing attacks?
Very good question. Yeah. So there you go. Troop includes at least a sandboxing feature. Could probably call it more time boxing feature, where you're giving it a function f and a time t, and then it will guarantee you that you will. It either will return the result of having run that function. It will pad the time needed, such that it actually takes the entire t time you want. Otherwise, it gives you an error if there's something crashed. Then it will tell you that this crashed in this time, or it will give you a continuation such that you can continue running it if you want to run the computation that takes longer than the t time you gave it. It seems right now that just using a t of 1 millisecond, which was the lowest I could set it to, was more than enough, because the hash map just never took longer than 1 millisecond to actually insert and extract something. So yeah, based on, I can't remember what the actual term for it is now, but by padding essentially the running time, such that it always takes 1 millisecond exactly, it seems to at least work for now.
More questions? So in terms of cryptography, is it just about using hashes, or in general, what kind of things do you use in Troop?
Are you thinking like as in like how to reference the different Troop values? Or what were you thinking about, like what we're using? I'm sorry, I'm not entirely understanding the question.
So I guess you must use encryption, signatures, things like this to implement this IFC in terms of something distributed.
As far as I understand, with distributed systems, I'm also just switching over to this topic, so please, if someone can correct me, that would be nice. What are usually pointers is when you think pointers on usual machines in distributed systems, you always say cryptographic hash. So that's where we were thinking to begin to use a SHA string of the value. And otherwise, everything is built on top of a peer-to-peer library, which also includes lots of cryptography to actually ensure that you're actually speaking with the other peer you actually wanted to speak to, and no one was like trying to impersonate someone else. Yeah. So there's a lot of cryptography going on underneath. Luckily, most of it we don't. We just use. Yeah.
Okay, so if there's not more questions, we stop here and the next speaker can prepare.
Can you hear me? Yeah? Yeah. A bit again? Oh, okay, that's good.
The next talk is by Pierrick, and he will tell us about GNU 0.
Thank you. So hi everyone. So I'm going to talk. So I'm Pierrick. Thanks for the introduction. So I'm going to talk about our tool. So it's GNU 0. So it's a compiler-based zeroization static detection tool. So it's based on GCC. So first a bit of context maybe. So what's zeroization? Well, zeroization is the action to overwrite any sensitive data you might have in your program, such as password or cryptographic keys, with zeros or any other dummy values. And here you have a small C program where you can see that there is a password allocated on the stack. You read the password from a user, you use it, and finally you use the memset function to actually overwrite your password with 0. So you are zeroizing it, basically. And so when talking about secret, you also need to take into account what's called the secret dependency. So that means your secret, well, then might propagate to other variables during your program executions. So here, for example, you have a small function which has 2 variables. So the secret variable, which is secret by name, and the X variable, which is secret, which is dependent on the secret. And so even though you correctly zeroize the secret, well, at the end of your function execution, X remains on memory, and so its value still leak, well, might leak. And so zeroization matters because your secrets, well, you need to explicitly override them. Otherwise, if any memory disclosure bugs happen, well, you can have a leak of them. So for example, in those vulnerabilities, so for example, Hotbleed, which is a quite old vulnerability now on OpenSSL, but more recent vulnerabilities, for example, such as on the KeePass password manager, but also on the GNU Linux kernel authentication module, PAM. And so in C program, to be able to erase your data, so to zeroize them, you have some requirements. And one of them is that you need that your data has to be programmatically accessible by your program. So that means that your variables holding those data, they need to be in scope first, but they also need to be accessible. So those data need to be accessible without undefined behavior, such as you cannot access data behind a freed pointer, for example. But beside those requirements, you also have some problems, such as the fact that compilers are quite aggressive regarding optimizations. And for example, they are more and more aware on memset-like functions. And so they might just remove calls to memset functions if they see that the variable you're using with the memset function are not read afterward. And so that's known as the death store elimination problem. But another thing is that the fact that, well, programmers are human beings, actually. So it's kind of easy to get it wrong. You can simply, well, forget to insert zeroization mechanism or misplace it. And so in C, it's due to the fact that, well, zeroization is manual. So that's make it fragile and error prone. And so it's true that there are some tools that exist, but so static analysis tool. But according to some surveys from both academic and industrial worlds, well, developers have workflow, so they have habits. And so if a tool needs developers to break their workflows, then it will likely refrain its adoption. And another point is that the diagnostic of the tool is important. So if a tool has a complex or a noisy diagnostic, it's most likely then the developer will not lose time to understand the diagnostic itself, hence refraining the adoption too. And actually, those 2 points are usability issues if you think about it. And so we try to say, well, okay, so GCC is already part of the developer's workflow. And actually, its static analyzer introduced in 2020 already implements a quite nice reporting system, as we will see. Also, GCC, so the GSA, so the GCC static analyzer, is aiming for sound analysis. Hence, we developed GNU0, which is a tool to automatically detect missing zeroization in C programs. So as I said, it directly integrates into the GCC compiler through its static analyzer, so the GSA. So we needed to modify its internal a bit to fit our taint model. But thanks to its position within the compilation pipeline, so the GSA position within the compilation pipeline, GNU0 is optimization aware, which leverages the detection of dead store elimination. And we focus on two distinct, two related weaknesses, so the stack and heap based zeroization failure. And GNU0 will track sensitive data from its declaration to its end of lifetime. And so we still need to know what is secret because it is context dependent actually. So we designed two attributes. So there is the scrub attributes on one hand, which helps identify sensitive variables, so the variables that will hold your secrets. And also the scrubber attribute, which helps identify effective zeroization functions. Because the goal of GNU0 is not to verify the effectiveness of zeroization functions, but rather to detect if there are zeroization mechanisms in your program. And so GNU0 relies on the symbolic execution of the GSA and taint tracking to follow sensitive data across function calls, but also through named and temporary variables that might be created by the compiler during the compilation. And so it's interesting to notice that since we are at the really late stages of the hardware and language independent intermediate representation, in GCC, well, every variable might be in memory or in registers. So we do not make any distinctions between memory and register here. And so GNU0 will emit any warning if any value, sensitive value, reaches the end of its lifetime as being unscrubbed. So here you have a small example where you see on line 8, there is the foo function, which has a secret within the y variable. So that variable needs to be zeroized. You see that it's passed by address to the bar function, and finally on line 11, it's effectively zeroized through the zeroize function, which is marked as being an effective zeroization function. But the bar implementation is actually dereferencing its argument. And here you have the value of your secret, which is leaking in the stack of that variable, that function. And so here you have an output of the warning issued by GNU0 within an IDE, which is VS Code, thanks to the serif format. And so you can have here a glimpse of the diagnostic system of the GSA. So you can see that there are several steps. And each of these steps is linked to a location within your source file. And so you can see that the first step is the entry to the foo function, then you go to the bar function, and finally on step 6, your secret is leaking. So to be able to do that, we designed a taint model which is different from other tools, because we make the distinction between two kinds of variables, of secret variables or tainted variables. On one hand, we have the source variables, which are the ones that are explicitly marked with the attribute scrub. And those variables can only be destroyed by a call to an effective zeroization function. And on the other hand, we have the tainted variables, which are all the variables that depend on tainted data. And those can be destroyed, so their taint can be destroyed either by a call to an effective zeroization function, but also by assignment. So here you have a transition table of an assignment, depending on the state of the left-hand side of the assignment and the right-hand side of the assignment. So if the left-hand side of the assignment is in the state source, so if it's a source variable, so a variable marked with the scrub attribute, then we don't really care what's on the right-hand part. The new state of the LHS will remain a source. But if it's untracked or tainted, well, we will look at what's on the right-hand part, and this will define the new state for the left-hand side. But defining a taint model is not enough, because we still need to define a leakage model. And so we went for variable lifetime. So we distinguished between two different lifetime here. So we have the stack variables. So those are the variables that are tied to a function scope. So basically, those variables need to be zeroized before your function returns. And on the other end, you have the heap variables, which can be more tedious because they might live throughout several functions. And those variables need to be zeroized before a call being passed to free or realloc, for example. And so if a sensitive value reaches the end of its lifetime as being unscrubbed, it's a leak. It's interesting to notice that GNU0 does not need program termination, which leverages the analysis of driver code, for example. And this is because the analysis is occurring during the symbolic execution and not afterward. And so, as I said, we needed to modify the GSA a bit. So here you have, for example, two variables, so the secret and the y variable. So only the secret variable need to be zeroized. They both have the same assignment, so for the value 42. And on line 3, we want to know, well, is y in the unscrubbed state? So that means, is y waiting to be zeroized? And the answer should be no. But actually, the analyzer, so here you have a glimpse at its memory model. So it's mapping, it's actually a map between what's called region and S value. So you can see region as the memory cell holding your data, and the S value being the content of this memory cell. And so here you have both the secret region and y having the same S value. And so when you're implementing an analysis within the analyzer, well, you're actually mapping the S value of that variable. So here we will tracking the state unscrubbed for the value 42. And so here on line 3, when we will ask to the analyzer, well, what's the state of the variable y, when it will look its S value and look within the map and say, well, this is waiting to be zeroized, which is a false positive in our case. So we modified the analyzer to also be able to associate states with the notion of region, so the notion of memory cell itself. And so to keep away our modification of the GSA, well, the GSA itself, so the GCC static analyzer itself, was really designed to track states, so to analyze pointers itself, rather than regions, so for example, integers. So that's what's here. So that means that it was meant to track for S values, because the memory model itself actually gives you a 3.2 analysis thanks to the model of the S value and the region. And so we tested GNU0 on different level. We tested it first with unit test to assess its taint model, our taint model propagation, taint propagation model, sorry. But we also ran it on the NIST Juliet test suite, so specifically the test for the stack and heap zeroization failure, and we had 100% detection rate. But we also ran it on different real-world code base, so different kind of code base actually, so with different optimization level. So we ran it on the libsodium cryptographic libraries, but also on the GNU Linux kernel crypto models, specifically the implementation of T and S, and also on the GNU Linux kernel, GNU Linux, the WPA supplicant driver. And we found some issues in the 3 code base. And so just to conclude, well, our work on GNU0 showed that, well, the analyzer, so GSA, is very suitable for analyze real-world code because we were able to analyze cryptographic libraries, but also non-terminated code, such as the WPA supplicant driver. And of course, we have some compile time overhead, but that one is tied to the contour graph complexity of the code, and only in the case where warnings are issued by GNU0, because the GSA is actually doing some past feasibility computation, but in a lazy way. So yeah, thanks for your attention.
Thank you. So we have time for questions. First one was here.
Thank you. My question is, how crucial do you think the placement of the analyzer in the pipeline is for detecting the important optimizations and missing things that might happen in the backend, etc.?
Yeah. Well, it cannot detect a thing happening in the backend because it's just at the really late stage of the middle end, actually. It could be really interesting to try to put it on the backend. So I think it might. So depending on the backend, actually, you might have some false positive, totally, yeah. But most of from what I saw, because I didn't dig into the backend of GCC that much, because it's quite complicated, but from what I understand, most of the optimization, so most of the dead store optimization are happening in the middle end. And so you have some optimization for certain architectures, but yeah. So in those special cases, yeah.
Yeah, I would assume the problem is that in optimizations, the fact that the lower rings might not do easy things like zeroizing a variable by assigning to it is a bit edgy. I'm not sure it works most of the time.
Yeah, yeah, I'm not sure it works either. And also link time optimization is after again. So yeah.
If I understand correctly, for the stack allocated variables, you individually scrub the variables that are marked to be scrubbed, right? At the end of the function.
Yeah, if they are marked, yeah.
I was wondering what would be the overhead, at least for reasonably sized stack frames, just to scrub the whole stack frame at the same time, and then you can use a very optimized loop for doing that.
Yeah, well, there's actually an implementation for that within the GCC compiler. It's an attribute. You just have to put it on your function, and it will basically scrub all your stack in your function. I'm not sure if there is the same implementation in Clang, but yeah. It might be doable, yeah. To do it yourself, I'm not sure, because if you do it yourself, you're yeah. Yeah.
Okay, so last question. Maybe the next speaker can already prepare.
At some point you mentioned GSA aims for soundy analysis.
Yeah.
What does soundy mean?
Soundy analysis is for neither sound nor complete, but rather go for something that is close to soundness without proof, or it might have proof. But in the GSA case, there is no proof at all. Yeah.
So let's thank Pierre. Okay, so next talk is Yanis, and he will tell us about tooling design for long title.
Yeah, indeed, a pretty long title. So the idea is to talk about tooling design and things we've learned when we designed some systematic evaluation to evaluate the preservation of security properties at low level after compilation. So first, a bit of a recap of what we are trying to present here. So we're talking about systematic analysis of low-level security property after compilation. So this is critical for a lot of software analysis, and a lot of the software you're going to analyze may be vulnerable to some type of low-level security properties, in particular side channel and fault injection attacks. And the resistance against some of these need to happen after the compilation and the code will be actually executed. So this is not always the binary code. Sometimes you can have optimizations that come after the binary code. But here we will focus on the software side of the problem, so by analyzing binary code. And so in particular, this can help to check if what the compiler does up to the end, if it preserves some countermeasures that you have introduced either at source level or during compilation, and if it did not introduce any additional vulnerabilities. So what we believe and what we have been tasked to do for academic research and for industrial partners is to check automatically that these properties are preserved on some type of verification. So in the first step, by thinking about this, you can think that this is a very simple thing to do. You have a set of program collection for which you have to analyze a given security property. So you give the property, you have a set of compilers, you take your program and you go through the compiler to obtain your binaries. Then you send these binaries and your security property to your analyzer that is able to handle this. And your analyzer is going to say, yes, the property is verified, or no, it's not verified. Well, unfortunately, in practice, if you want to design this type of analysis, you're going to encounter a lot more issues, and you're going to have add a lot more tooling and configuration in order to be able to make this work. So some of the key problems I'll talk about in this presentation are the handling of the parameters of the security properties, typically public and secret data, especially in programs when they are not given explicitly, and all the details of the compilation chains that you use in order to obtain your binaries is going to be an issue in order to systematically analyze the program you consider. So typically, what is the step from going to the source benchmark you're given for the analysis and the final experimental setup? So for this presentation, we are going to discuss the experimental setup we have built with the symbolic analyzer PriSC, which is a binary level symbolic execution that is able to handle a variety of low-level security properties, including side channel, constant time, zeroization, fault injection attacks, robustness, this type of properties. We are going to tackle two benchmarks which have been presented in open research and requested by industrial partners. And we will see for all of this benchmark what could be automated explicitly during the design of the toolchain and what had to be done manually in the end, which means that at some point you have to say explicitly for this program you need this specific property. So a first benchmark you consider is a set of constant time and secret erasure evaluation. So the starting point is an initial work by Leslie and Daniel that was published in 2022, in which they had a set of some primitives from cryptographic properties to evaluate constant time and secret erasure or zeroization properties on, which came with a common test harness. So the idea of the common test harness is the one that is presented in this schematic representation. Basically, you try to create a program in which you will call the specific code you want to evaluate and to systemize the evaluation by using this specific harness. And the request was to extend this benchmark along 3 lines. So first, add additional primitives, so coming from different libraries. Add additional targets, so typically evaluate the security of these primitives on a lot of different architectures. And possible adaptation for primitives that were compiled from other programming languages, in particular Rust. So what were the issues in order to automatically analyze this code? First, so the use of the common test harness is very practical, but it has some issues in particular because you will need to be able to manually remap the function you want to evaluate within the test harness, which means that if you have a simple function where it's easy what is going to be the input and the output, in particular where the secret and public data will be able to be sent, you will be able to easily map the test harness. If you have more complexity with this, and we'll see an example later, you will have trouble in order to propagate the secret and public data you generate in the test harness correctly within the example you evaluate. In order to simplify the evaluation of the binary, there is a lot of initialization that you want to avoid, in particular a lot of the initial state of the binaries. So for this, we use the core dump evaluation. We create a core dump at the beginning of the execution. And then you need to manually set, in particular, the size of the public and secret data in order to map this evaluation. Then you have some considerations that you want to evaluate. Typically, that some code will not be able to be compiled for any target. And if you want to reuse as much as possible of this work in order to evaluate code from different languages, you can use some mappings, but it also comes with a few issues with the results. So with this, you can have an automated evaluation, and you can have such things are nice table like this, but you see that you have issues. Typically, you have all the things in gray which are incompatible targets. So typically, these are programs that cannot be compiled either by a given compiler or to a typical target. So typically, if you have a zeroization process that uses a specific x86 instruction in order to evaluate the issue, you will not be able to compile it for another architecture. The other thing that can happen is that the issue you get with the test harness is that different compilation setup will lead to wildly different results. So typically here in 2 lines between the A and the B, you have the same evaluation of some zeroization functions, but depending on whether you link them directly within the code or whether you link them through a library, you will have very distinct results in the evaluation. So some will create a much more unsecure code, whilst in the other case, if you link through a library, the compiler will prevent a lot, you will manage to prevent the compiler from removing a lot of them. So now let's go through a second benchmark of constant time evaluation. So here the starting point was a collection of post-quantum cryptographic algorithms, so typically key encapsulation mechanisms and signature algorithms. And the request was to evaluate the capabilities of BinSec in order to find if the tool is able to detect, to evaluate the constant time property of this code. So the idea was to evaluate different compilers and different targets. And we had exchange with the developers of the primitives, typically for the candidates of the signature evaluation, to report the vulnerabilities we found. Some of them were found interesting, and some of them were found useless. We'll see why in a bit. So in this case, with the post-quantum cryptography algorithm, the key point is that the test harness is pre-existing, because you have the standardization from the evaluation process of the NIST for the candidates, from which you get evaluation test harnesses in which all the secret and public data are set, and in which all the evaluation, at least a common call scenario is evaluated. So the idea with this is that you will be able to use this test harness in order to compile, to evaluate the primitives, as long as you're able to compile a given primitive to a library with the given evaluation. And this is where most of the difficulty comes for this, is that adapting the compilation process to handle a different compiler or to handle a different target can be very painful, because each primitive is going to use a wildly different toolchain for compilation. So this can be, in the best case, makefile, cmakefile, stuff like this, but it can also be a cryptic shell script which hardcode the given compiler and options that are automatically generated. So the second thing that can be an issue with post-quantum cryptography is that data passing, so public and secret buffer, are standardized, but the content of the data is not always correct, is not always standardized. So typically, the secret buffer can contain public value. And then you can have some scalability issues, which means that your analysis, your setup for automated analysis should be able to handle the ability to actively tweak your analyzer. So for example, as I said, the standardized secret buffer can contain public data. So usually this will be a public hash of the secret data, but in some schemes it can be a lot of various possibilities. So typically this will come from the fact that you will have an issue with your public data, but if that's the case, sorry, I lost my thought. Yeah, so you need to find the details of what is public and what is private directly within the reference documentation, which can be a pain to set up. And the other issue you're going to have is that you have some of the results you're going to get that are going to be proved useless because they do not depend on the correct setup. So one of the things that can happen is the evaluation of useless targets, typically a check on a key that is going to be equal to 0. But you also have in post-quantum cryptography systems like key extension mechanisms or key generation, detailed key generation mechanism in which the secret is introduced during the computation. So same thing, you can obtain nice results, but you will have some scalability issues with a lot of setups. So as a conclusion, what we can say is that the systematic evaluation of low-level security properties can be done, but you have a lot of tweaking to do in the analysis in order to obtain the detail of the parameters of the security properties that you want to do. And while this can help finding existing vulnerabilities and build safe or unsafe guidelines for evaluation, you have a significant part of this evaluation that still has to be done manually, and for which we will have to design most likely standards in order to be able to detail what is the public and secret data, typically for constant time, and how are these data evaluated during the evaluation. So now, thank you for attention, and I'm open for questions.
Thank you. So first question was here.
A quick question for that last open question is how to specify secrets and etc. in the program. Would you think debug information could carry that info for you if the compiler supported it?
Yes, so it's one of the possibilities. If at some point in the compilation chain you have this information, being able to propagate this information up to the final evaluation is a very good idea.
All right, thank you.
Next question was here.
In your previous slide, when you're talking about useless results, is it, that was this one, would some form of declassification be useful there?
So typically, yes, what we could work on is some type of either post-evaluation or respecification to some details. The usual idea, so what we had in the exchanges with the developers was part of the evaluation for which we badly configured the evaluation. So typically, we reported evaluation due to the fact that we did not understand that part of the secret buffer was public. So we reported violation on public data. And then you have this type, so typically rejection sampling evaluation, from which we will only know that the key has been rejected and do not learn much information. What can help here also from the developer's part is correctly detail what is protected and what is not protected, or in particular what could be or should not be evaluated.
Okay, more questions?
Do they also use some blinding and masking, things like this, that would, make the analysis also useless, because then you can't leak anything? But
it's part of those things. So in those ones, those are not cases that we reported, but indeed, if you have some mask function from which you do not want to report evaluation, or typically if you work with hashes of the secret keys that are not relevant here.
Okay, so maybe one last question while the next speaker prepares. The next talk is Søren, and he will tell us about decompiling for constant time analysis.
All right. So I'm going to talk about constant time analysis and how you can use or cannot use decompilers for that. So before we start, I'm going to make a short introduction into formal side channel security, where I talk about the setting where the attacker and the victim are running on the same machine, and the attacker wants to get some secret values from the victim. Of course, the operating system forbids just accessing the data directly in the memory. But because we are running on the same machine, we will have side channels via hardware microarchitectural features like caches or branch predictors. And when the victim executes, you will leak some values to that. And all the attacker has to do, even though it's not that easy, he has to observe the values that were leaked in order to see some secrets of what we have computed on as the victim. And in the formal settings, what we want to do is we want to model the victim, right? We give the attacker arbitrary power, and we just want to formally model how the victim executes and what he leaks. And for that, there's constant time leakage semantics, which is just standard operational semantics. So we do not model like microarchitectural features like caches explicitly in the state. Instead, what we do is we attach the semantics some leakage annotations that every transition will give out. These are the observations that capture the leakages that we would send to the microarchitecture state. And that depends on the leakage model that you're looking at. In case of constant time leakage, this will be dependent on the executed instruction at each step. Being a load or store, it will leak the memory address of the load or store to through the cache. Or for conditional branches, you will see the branch outcome in the microarchitecture. So the security property that will ensure that no such attack is possible is called constant time, which means a program is constant time when for any two initial states that look equal to the attacker, so they are only different on secrets. When we run both initial states, we will collect the leakages along our formal semantics, and then these leakages have to be equal as well, because that means that the leakages that we observed do not depend on secrets, because our initial states were only different on secrets. All right, so the scenery becomes like this. On the left, we will just use a constant time program. Oh, this should be been the victim program. We just have to make sure this is constant time. And then the leakages that the victim will make are harmless because they do not depend on secrets. So basically everything we have to do is we have to make sure our program is constant time. And for that we can employ constant time analysis tools like PriSC, which we have just seen presented. Oh, yeah. All right, so the basic idea is we just take our crypto library, we send it to the analysis tool, and it tells us constant time or not constant time. Well, it might not be that simple. What we are really interested in are the binaries, right? We want to make sure that the binaries do not have constant time attacks. So we're asking ourselves this about the binary. What if your constant time analysis tool is a source level analysis tool? Well, you could come up with the idea to just decompile the program and test it then, right? But the question is then, did you fuck up? Is the binary still constant time, or did your decompilation program do something wrong? Let's look at an example. This is MLKM crypto primitive, and I'm not going to go into the details, but it's a binary. What is important is this part, where we have a bit test on a secret message, and then we do a conditional jump on the result, which means we will leak a secret bit of the message. Well, when we decompile it with, for example, reddeck, we will end with a code like this, where the highlighted part is corresponds to the bit test. And what we see is we no longer have a branch like a control flow branching, right? We have a conditional move here, which means the hardware microarchitectural features that would capture this leak will not capture this. So we have removed our leak from our program just by decompiling. So the scenery becomes like this. We have our binary, we decompile it into a constant time program, which means our CT analysis has no other option but to correctly identify the program as constant time. And that means that our decompilation part was unsound. And we've tested several decompilers, and they all have soundness issues regarding to constant time, which is not a surprise when you are real, because decompilers do not really care necessarily about constant time. All right, you might say, scrap that. I'm just going to use the binary tool, right? I'm going to use this constant time analysis tool that it works directly on the binary. Now, when you look inside of the tool, usually all of them, no, usually, that doesn't work, okay. But usually they will transform the program before as well, right? They will bring that into an IR, into an intermediate representation on which they can operate better. And they will also do some optimizations in order to reduce like the analysis time that they have to do. And then they might analyze it, and indeed, they will also say constant time in some cases. And we've identified this in 2 different tools, CTVerif and BinSec, though I should note that what we used was not like a binary from a real cryptographic library, but we handcrafted some examples where we thought like, okay, maybe this goes wrong, and it actually did. But nonetheless, right, you wouldn't want to have that in your tool. So let's look at the general setting. The general setting is that we have some binary, we decompile it, or if you want to say even more general, we have some program, we transform it, and then we have a target program. And what we would like to have is a little bit more formal intuition on what is a sound way to do this. And we have identified 3 properties: reflection, preservation, and transparency. So reflection says, well, your input program, if that is not constant time, then your output program should also not be constant time, which is the same to say, okay, our transformation does not remove any vulnerability. Preservation is probably already a little bit known to some people here. It's just the opposite. It says if your input program is constant time and I transform it, then the result is constant time. When you think of a compiler and you have a source level program that is already secure, this is the property you would want. And then transparency just combines both and says if and only if, right? So we neither remove nor introduce vulnerabilities. And with that, we can go to this picture. And what we want to do is, at this point, we want to use transparent transformation, because then we will get a non-constant time program that we actually can analyze. And that part here is sound. All right, let's look at how we know the property that we want. How can we prove it? Like, I have a transformation, how do I prove it? And before we do this, let's look at the particular preservation and reflection individually. And we're going to start with preservation because this is a property that is already, as I said, known to the compiler community, right? And usually what we do in compiler security is we employ a simulation, right? We relate some run of the target program, and our simulation will give us a run of our source program. Now, in our case, our semantics has leakages. And for most transformation, it will be the case that these leakages will not be equal anymore. And I mean, think of a dead load elimination. The load previous to the transformation would have leaked some value. If we eliminate it and replace this by a no-op, for example, it will not leak anything anymore. So the leakages will not be equal. Now, for preservation, what you can do is you can employ a leakage transformer and make sure that whenever your simulation relates some source trace, you can actually explain the target leakages in terms of the source leakages. So you have a function that takes the source leakages and produces the target leakages. And that helps with preservation. So let's look at the constant timeness of our target program. We will look at the second trace with some leakages. We will simulate that as well. The leakages will be mapped by our transformer still. And because our source program is constant time, we have equal leakages along both traces. Now, because t is a transformer function, so a function, it will make sure that then also in the target program we will have equal leakages. And that means that the target program is constant time as well. So this is the idea of how one proved preservation. And like this is a result that we did not come up with. This was already a given, or previous work, I should say. How about reflection then? Now, if you think of it, the property, if you take the contraposition, is basically very similar. Now, if the target program is constant time, the source program should also be constant time. What we do is we just take the same approach. We look at the runs of the target program. We take the simulation and map them to runs in the source program or in the input program. But this time, we employ a reverse transformer. And the reverse transformer does not explain target leakages in terms of source leakages, but the other way around, right? You get some target leakages, and the transformer should explain the source leakages. And then what you get is when your target program is constant time, of course, your source program is constant time because it was a function. So what you get is a modified theorem, if you will, where now you need a reverse transformer instead. About transparency, well, we know how to prove reflection and preservation, so we could do just both of these, but we thought maybe we can do better. What we need is the following, right? We need a simulation and we need a transformer and a reverse transformer. The transformer maps from source leakage to target leakage, and the reverse transformer maps from target leakage to source leakage. And the idea that we had is, well, on the left we already have many of these transformers. For example, in Jasmine framework, these functions, precisely these functions, are already defined. And for the reverse transformer, this is the ones that we want. What if we can just flip them, right? Flip T around to get U. Then you don't have a lot of work. You just can flip T. And then you can use T inverse. Now there needs to be a condition, so this is possible, right? You cannot just flip any function. The function must be injective. And that's basically the idea that we have, right? Like, just make the function injective. Now, this is the core idea, and it works precisely like this. But depending on how your simulation looks, and if it is not log steps, you need a little more details there. I'm going to skip it because the talk should be a little short. So the resulting theorem that we get is, all right, you have your simulation, and now what you need is just the transformer that you already had, but you have to make sure that it is injective. And then you get transparency for free. And we applied this to quite a few transformations just to see that leakage transformers are actually injective in some cases. And we found quite a few cases. We think this is promising to do more. All right, so this is the theory part done, basically. And we thought, OK, now we have this nice idea on transparent transformation. Can we make something work in practice? And we decided not to go with a very formal approach and make it in a rock. Even that would be very cool, but it takes a lot of time, and we wanted to do something that we can evaluate. So what we decided is to take RedDeck, the decompiler, and make it more transparent. I'm saying the transparent here, but it is more transparent because we do not have guarantees. So we started with handcrafted likely to fail snippets because we already tested the tools and found examples where they fail. And we took every pass of RedDeck individually and let it run on the snippets. And then we analyzed the outcoming snippets on did this pass behave transparently on our snippets? If yes, we kept the pass, and if no, we removed the pass from RedDeck. And then we called that thing CT RedDeck, right? The passes that survived. We tested it on a benchmark of binaries, which we did not, of course, not use in order to train or in order to test the passes. And we got the decompiled binaries, and what we saw is that this was already sufficient to make it RedDeck transparent on all the vulnerabilities that we found in our, that we had in our test set. To comparison, RedDeck already removed 45 vulnerabilities from them. To wrap up, we've seen that decompilation for CT analysis is unsound generally. We have seen a formal property that we can employ for the transformations that we do prior to analysis that will guarantee sound results. We have seen a recap on how one would prove preservation. And we have seen that injectivity of the leakage transformers is sufficient to gain transparency. And then we have seen how we can use the idea of transparency to make a more transparent decompile and analyze approach. OK.
Thank you. So first question.
Can you give a bit more details about RedDeck? Like what kind of optimizations does it do?
Oh, quite a lot, actually. I mean, it's like 60 different optimizations. About 10 of them are analysis passes. These are do not change anything. They just analyze, so they are trivially working. because they don't do changes from the rest quite a lot. They borrow a lot of passes from LLVM framework. So there's LICM, there's sub-expression elimination, I think is in there. They have dead code elimination. I mean, very standard transformations, I would say. It's
and what? I don't want to steal time.
Okay.
Thank you. Kind of open question. Do you think there is anything specific to the decompilers that could break constant time that we wouldn't already find in the compiler?
I mean, the difference is not necessarily that the passes are different. I mean, there's probably like one thing that you don't have in compilation is like the recovery of control flow. This is something that you have in decompilation, but we could prove that in our framework, we could prove that that part is transparent actually, unless your analysis messes up big time. So if if you can recover control flow, the transformation will always be transparent. Apart from that, I don't think so. The passes are very similar, I would say.
Okay, thank you.
There was one at the back.
And one difference is that when you're thinking of compilers, you often think about preservation, right? And when you think of decompilers, it's reflection. But if you want perfect compilation in that sense that you have transparent transforms, then it's similar, yeah.
I'm just a little confused. So RedDeck is just a decompiler. Did you invent your own leakage transformers for this?
Again, sorry?
Did you invent your own leakage transformers for each pass of RedDeck, or was that already part of RedDeck?
No. For the passes that I showed you back here, that's too far forward, backward. I'm sorry. All right. So for the passes here, we did show that you can flip the functions around, the transformers around. For RedDeck, what we did is we did not formally prove the passes correct, but we tested them on the set on likely to fail snippets. And then if it behaved intransparent on these, we just removed the pass.
Okay, so time for one last question before the next speaker sets up.
Hi, thank you for the talk. So I'm curious, how hard is to find these leakage transformers?
I mean, I would say it's more difficult to find the simulation for a compiler pass, right? If you have a formal definition of your compiler pass and you already have a formal definition on how it transforms a program, and you have defined your simulation, you will immediately know how the leakages will be transformed, because usually a compiler pass where you have a simulation doesn't like, the simulation usually has very thin slices of code that it is looking at and relating. And therefore you will mostly know quite fast whether the function that you see is injective or not injective.
Okay, so maybe really last question while the next speaker is actually setting up and getting a mic and everything.
So you didn't have to tweak any of the pass in there. You just removed when it.
We just
didn't
removed
pass.
them, yes.
Okay. Because I could imagine instead of and then you wouldn't even have to prove transparency. Maybe it's not very clear, but
I'm not sure whether I understand. But you can chat afterwards if you want.
Yeah.
Okay, just as an announcement, does anyone have a USB-C to HDMI adapter here?
Last talk of the session is Shinyu, who will tell us about modular verification of probabilistic constant time.
Yeah, thanks for the introduction, Kevin. My name is Xinyu Xie from PISP. So the topic I'd like to discuss here is modular verification for probabilistic constant time. Before I really start, I want to mention that I will not go deep into the intricacy around the probability, but focus on the modularity. So probability is kind of essential for cryptography, but it's very intricate for verification. And our approach here is very general. It's applicable to both deterministic setting and probabilistic setting. So we can think from deterministic point of view in this talk, and I can explain offline if anyone is interested. Okay, let's start. Let's start from the boring question, which is already explained. So what is constant time? Constant time is a discipline for cryptographic implementation. It is to mitigate a class of side channel attacking. Constant time means that the adversary cannot infer secret information by observing branch decisions and memory accesses. So on the right side, I explicitly marked what will be leaked to the adversary. In other words, constant time means that the leakages have no secret information. So to prove constant time, an important property is modularity. By modularity here, I mean the modularity along function calls. Here on the right, there is an example. This is a common utility in cryptography. So reject sampling, very imprecisely, reject sampling means that we want to produce a sampler of a small domain from a sampler of a large domain. So it contains a loop. The loop keeps generating random numbers until it's within the bound. So this reject sampling function is used everywhere in cryptography. So here, by modular verification, what I mean is that we want to first prove that these utility functions are constant time. Then we go up layer by layer. When we are proving callers are constant time, we want to use the established results of the callees. Why this modularity is important? So in this way, the proof will become more structural, and it will be very easy to understand and maintain. And it's also it's reusable in a very natural way. Then the question is how we can prove constant time in such a modular way along function calls. Following the practice in information flow security, the natural first step is to provide contracts for every functions. So the contract labels every input and output by public or secret. But public means that this information is fine to be observed by the adversary. But the meaning of secret will be a bit tricky. One may think that secret means that this information cannot be known by the adversary at all. But sometimes it's not the case, because public output may dependent on secret input anyway. So for example, consider a hashing function. So the hash result is computed from the secret input. But by the property of a hashing function, we know that the hashing result is fine to be leaked to the adversary. So then how we can describe what constant time with respect to this contract really means? One way is to describe it as a comparison. We say that the leakages have no more secret information than public input and public output. So I call it as a modularized constant time. To prove this comparison will be a bit tricky, especially in probabilistic setting. But what's more interesting here is how we can use this established contracts. So I will give you my solution and the intuition behind this solution, and a connection behind this solution. So the solution here is actually very simple. So when we are proving the caller, we can replace the function call by 3 statements sequentially. First, leaking the public input. Second, calling an ideal function. This ideal function is semantically equivalent to the original callee, but has no leakage. Third, leaking the public output. So on the right side, this is how we deal with the reject sampling example. So we explicitly leak the public input, which is the bound, and we directly call a mathematical sampling function which samples in this interval, and then we leak the sampling result, which is public output. And the theorem on the left says that if all the callees are modularized constant time, and this replaced caller is also modularized constant time, then we can know that the original caller is immediately modularized constant time. So why this theorem is sound? I will tell you an intuition. The intuition is the transitivity of the inequality. So what does this contract say? This contract says that the side channel leakages during the execution has no more secret information than public input and public output. So we can use this public input and public output as the intermediate value of the comparison. So here, by explicitly leaking the public input and public output of the callee, and prove that these leakages are actually no more than the public input and public output of the caller. So these leakages have these leakages do not have too much secret information. Then we can show that the leakages overall do not have too much information, too much secret information. So this is the intuition is a transitivity. But why we need an ideal function here? The reason is that we want to compute the value of the public output. So we need a function, and this function should not bring any extra leakages. That's where this ideal function comes in. Yes, so this is the solution. And I want to tell you more behind this solution. So I think behind the solution there is a connection between 2 fields, and the theorem above is actually an analog of a standard result in another field. So the field is multi-party computation. This is a class of cryptographic protocols where participants collaborate together to compute a function while keeping their data as private as possible. So what's the connection here? The connection is there is a correspondence between the basic security form of multivariate computation and this modularized constant time. So the basic security form of multivariate computation says that it also says that the intermediate values some intermediate values during the execution have no more secret information than part of the input and part of the output. So this is almost exactly the mathematical form of modularized constant time. So based on this observation, my theorem above is actually a transfer of standard modularization result in multivariate computation. So this theorem is called sequential modular composition. So it's published in 2000 by Ran Kennedy. This is the previous paper of famous universal composability. And as far as I know, this is widely used when cryptographers design and prove multivariate computation protocols these days. So this is the interesting connection. Overall, here I give you a callback contract style modular verification approach for constant time and the probabilistic constant time. This is a project at a very early stage. So for the future, the natural next step is to do evaluation and to see how much proof effort we can really save by this approach. And actually, this approach is not specifically bound to constant time. It can also be generalized to non-interference, as one reviewer pointed out. Yes. So that's all. So I'm very happy to take any questions and any feedbacks.
Thank you, Shiru.
Thank you. So thanks for your talk. I just wanted to mention, there was already in the past someone, I think Marco Badrignani, who saw a connection between universal composability and secure compilation.
Yes.
So if you, I don't know, do you plan to define a relational Hall logic to prove that your compiler is secure? So this would work for, as you said already, a very large class of properties, not just non-interference.
Yeah, so I saw the papers about secure compilation, robust compilation, and universal compatibility. But here, so first, this work is not about compilation. So this work is you can see it at source code level. So we are proving like source program satisfies constant time. So they are not like technically not. So the two connections are not the same. But so there is also an interesting question is that if we have this approach and we have like a secure compilation, whether these like two analogs of universal composability can be connected. I think this is an interesting question, and I don't know the answer.
Thanks.
Okay, are there more questions?
Sorry, I'm very not familiar with probabilistic constant time.
Mm-hmm.
I was wondering, how are you gonna, in which tool are you gonna implement this? Will it be on top of Jasmine and in EasyCrypt?
EasyCrypt.
Because there is already UC support in EasyCrypt, so will that be different?
So in EasyCrypt now EasyCrypt has probabilistic relational Hall logic, yeah. And it supports probabilistic. So it supports probabilistic constant time, mm-hmm. But it lacks of the modularity.
And isn't it sufficient to then use what they did in the UC support for EasyCrypt plus the probabilistic relational Hall logic and to get the modularity? Or
first the UC support for EasyCrypt is to use EasyCrypt to prove the UC of the of some cryptographic algorithms, mm-hmm. and here what we need is to improve the verification approach. So why the like why current easy equivalent does not support this. The reason is that here, if we want to say the leakages have no more secret than public input and public output, basically we this is more like an intuition. This is natural language. So if we want to formalize it, there are several ways. One way is to use conditional probability. And right now, EasyCrypt cannot reason conditional probability. So I think this is a difference. Yes.
Okay, so we have time for probably last question.
Sorry. So by public output, do you mean something like a declassification?
This is a very good question. The answer is yes. So, theoretically yes, but so declassification can do something more, right? So, for example, we can declassify some value in a loop, and so maybe this loop will not go into the public, will not go into the output. But of course, there we can always convert what is declassified as public output, and also we can convert public output into declassification. So they are theoretically the same thing.
Okay.
Okay, so maybe one really last question. At least I don't think we're out of time. But if not, let's thank Shinny one last time. And we're taking a break.
Oh, I see. So you guys are already working on this crazy problem.
I just wanted to say that because we have one last presentation, we will do the lightning talks just after the last presentation of the session. So yeah, we don't keep you longer for no reason.
Okay, so let's start. So welcome to the hardware security session. So the first talk is going to be by Jonathan, and he's going to talk about FSLH.
All right. Yeah, thanks for introducing me. So I want to talk about FSLH, or Flexible Mechanized Speculative Load Hardening, quite a mouthful, which is a specter mitigation that I developed together with Roberto Blanco, Leon Ducrier, Sebastian Halbig, and Katalin Rizzo at the MPISP in Bochum. Is there anything? Okay. Right. So first thing we should start with, why FSLH? Why another specter mitigation? Well, the first thing to say is specter attacks have been around for a while, but they're kind of still a threat. There's like no mitigation that has completely fixed it. And in part, that's because existing mitigations often have like complementary strengths and weaknesses. So let's look at two, for example. We might pick Selective SLH by Shiva Kumar et al., which offers sparse protections at very low overhead, which sounds nice, except it's only for cryptographic code, and you might also want to protect something else. Or you might look at Ultimate SLH, which is exhaustive, which means it has very high overhead, but it is able to protect arbitrary programs. You can just throw it at everything. So we looked at those two, and we decided to do something in the middle, which we call Flexible SLH, and it's able to offer sparse protections for all programs, and so we published this at CSF last year. The other thing we wanted to tackle is that existing mitigations, if they have security proof, they rely on manual security proofs on paper. And so we provide the first machine check proofs actually for Selective, Ultimate, and Flexible SLH in some 4,300 lines of rock. So just to make sure that we're all on the same page with Spectre, here's the standard Spectre example. We have a small code snippet and an extract of our memory at the top, where we have a public array with 4 elements, and then afterwards in memory we have a secret, and our code performs a bounce check. Now, on real hardware, as most of you have probably heard before, an attacker can observe control flow and memory accesses. So here our attacker can observe the outcome of this condition, it can observe the index I, and it can observe the index j, which here depends on the array at I. Now, this should all be fine if the array is public. Unfortunately, well, we're reasoning about Spectre here, so we have speculative execution, which means instead of waiting for this branch condition, if we have something that's out of bounds, our CPU unfortunately takes a guess, executes this code anyway, here loads our secret into J, and then therefore leaks the secret to the attacker. So clearly this is something we need to prevent. So let's look at some of the previous work. We'll start with Selective SLH, which, as I mentioned before, applies to cryptographic code, and therefore has the advantage of being able to work in a CCT type system for cryptographic constant time. So here, we label or we type all our variables and arrays as either public or secret. And then the type system actually does not allow us to use secret values in positions where they could leak. So this is standard practice in cryptography. And so now Selective SLH leverages this. Firstly, it's a speculative load hardening mitigation. So it keeps track of whether we are currently speculating or not by storing this in a special register, here the register B. And it does so by updating this register with constant time conditionals with the same condition as the branches, so that even if the branch is predicted, the value of this flag will not be predicted. And then they can leverage this to mask the values that they read into public variables. So if the flag is set, if you realized you're somehow on the wrong path, you're somehow speculating, you just mask this to 0 in this case. Now, the selective part is that they don't need to do this for secret variables, because the type system already guarantees that nothing can leak from secret variables. So you could put whatever you want into a secret variable. So therefore, this yields a very efficient mitigation for them with only minimal masking. But it's only for a limited class of programs, only code which is in this CT type system. So on the other hand, we can look at ultimate SLH, where they don't have a type system. They just mask everything. And importantly, that means they have to mask indices, not just the loaded values, because the indices can leak. And they have to also mask branch conditions, which is what other work doesn't always do. Importantly, they also mask a lot of other stuff, but we don't model that. So their mitigation applies to all programs, but also has very high overhead. I think in their benchmarks 150%. So that's bad. So we want to find a middle ground between those two. So what we do is we reintroduce the security levels, but we now obtain them with a static information flow analysis. Importantly, that means we don't restrict the use of secrets and can therefore accept all programs. This also means we have to sort of combine the two masking approaches. So if the index is secret, we have to mask the index. If the index is public, we get away with masking only the value. And of course, we may also have to mask branch conditions, but only if those are secret. So that's sort of how we developed our mitigation. Now, the next question you should probably have is, if we want to prove that this mitigation is secure, but we do it for arbitrary code, well, our source program could be completely insecure. So what do we do? So actually, we take a look at our compiled program at the bottom, the one with our mitigation applied. And we take two executions that are run in speculative execution in two different initial states here. And this produces some observations here, O1 and O2. And if those observations are different, if we find any leakage in our compiled program, then we prove that this same leakage was already present in the source without any speculative execution. So it's not introduced by speculative execution. It's not a Spectre attack. In practice, we prove the counter positive, and we call this relative security. So just some quick information before we continue. In our attack model, attackers observe control flow, as in branch conditions and indices of memory accesses. So this is a standard constant time leakage model. And our attacker actually has direct control over the branch predictor in our case. So we just allow the attacker to supply directives that fully determine how we execute. We go a bit further. The attacker can even choose the locations of out-of-bounds accesses, because our language still has arrays, and we don't model a memory layout. And in terms of the speculative execution itself, we actually go with a forward-only semantics as introduced by Bart et al. So that means we do not model rollbacks. We do not track like rollback states. Once the attacker causes us to mis-speculate, we cannot go back to sequential execution. This may sound a bit weird, but they already proved, and we also have mechanized proofs, that the results actually do carry over to normal semantics with rollbacks, and it makes it a lot easier. Right. So again, here's the diagram we want to prove. We have our equal observations at the top. We want to prove that they are still equal at the bottom after we apply our mitigation. So our mitigation actually comes in two parts. We first apply some information flow analysis. Then we apply the masking based on it. So in between here, we do a neat trick, and we introduce a third level. We call that the ideal semantics. And we give the semantics speculative execution, but obviously a highly idealized model. In practice, that means that we do the masking in the semantics instead of as a code transformation. And we apply it in the exact same way that our code transformation would also do, which means it matches the behavior of the compiled program. It produces the exact same leakage, and we can prove this with just a backwards compiler correctness proof. We don't need to reason about both executions at once here. Then we also instrument that with dynamic information flow tracking, so that we can then prove relative security for this ideal semantics at the top. However, that also requires something much more important, which our annotations have to actually be correct at runtime. Unfortunately, we produce these annotations with a static analysis on the initial program, and during execution, we refine our states, we refine our program, and so this doesn't really preserve. If we were to rerun the analysis, we would now have a more precise outcome, so this is unsuitable for the proof. So we actually introduce a well-labelledness predicate, which if you want, you can see as typing for the annotations. So our predicate says that an annotated program is labeled correctly to go from some initial labeling, which we provide, to some final labeling. This mechanism then allows us to prove a lot of things you would otherwise do about typing. So for one, our information flow analysis produces well-labeled programs. So we supply the initial labeling here, and it gives us an annotated program and a new labeling. And then this annotated program has correct labels to go from our initial labeling to the final labeling that it produced. The more important thing is this property is actually preserved by ideal execution with respect to the dynamic tracking. So if our program was well labeled for this labeling and the dynamic tracking after one step updates to this new labeling, the remaining program is well labeled in the new labeling. So with that, we can start assembling our proof. This now comes in 3 parts. One is for once we start to misspeculate in our ideal execution, we can prove what we call unwinding. And this just says that without even reasoning about the source program anymore, the observations here will always be equal. That's just due to 2 things. Everything that we label as secret will be masked. So this is just fully deterministic. And everything that is labeled as public, due to well-labeledness, is actually public. And therefore, according to our dynamic tracking, it will be equal in both executions. And therefore, the leakage will have to be equal in both executions. Then, for the part before we start misspeculating, we just look at our source program, and we see that there's a one-to-one correspondence here. We haven't transformed the program. We have only added annotations. And so the behavior before misspeculating is exactly the same. And then once we assemble that, we get relative security at the ideal level, which we then compose with our backwards compiler correctness proof to get the full proof of relative security. So to sum up, we have a secure mitigation in that it has fully mechanized security proofs in ROC. It's general in that it accepts all programs with our analysis. And it's efficient insofar as it only inserts protections where needed. Now, we choose a middle ground between 2 prior works. It turns out we're actually just a generalization of both of those works. So we actually coincide with selective SLH on programs that are CCT. And we coincide with ultimate SLH if you just label everything as secret. That means that we obtain mechanized proofs for those mitigations as corollaries of our proofs. Right. There is some future work left to do, always. In particular, the big point here is that we don't actually have a practical implementation, and therefore no real-world evaluation of FSLH. Partly that is because we still have some quite big questions, such as when in an actual compiler can you even perform such an analysis so that the results hold for future passes, and also where can you potentially insert your mitigations so that it doesn't get destroyed by later passes. The other thing is we would like to eventually investigate other LLVM SLH implementations, or potentially other compilers as well. Now, obviously, if you look at a real compiler, that is far too complex for mechanized proofs, and we're investigating property-based testing as a compromise approach. And finally, this is only a mitigation for Spectre v1. So we're also looking at other Spectre variants. For example, there's prediction of indirect branch targets and of return addresses. And we currently have some ongoing work on the indirect branch targets. All right. With that, I thank you all for listening. And I'm very happy to take some questions.
So are there any questions? Well, if not, I have a question about, you mentioned you have a mechanized proof that rollbacks are not necessary. Can you comment a bit on this?
I mean, I can comment in general. Do you have anything specifically you'd want to know?
Yeah, why are they not necessary, and how do you prove this?
So, yeah, I'll just go with why we don't need to model rollbacks. The idea is that if you have an execution that exhibits some leakage, and this execution is something with a lot of rollbacks in between, we only care about the first instance where our observations differ between the two executions. The moment we find a difference, we have leakage. And so at every branch, we can just ask ourselves, is the leakage in the misspeculated part, or is it later? And if it's in the part that gets rolled back, then we don't care about what happened after the rollback, so we don't need the rollback. And if it's after the rollback, we don't care about what happens before the rollback. That part wasn't relevant to actually exhibit the leak. Yeah, this was already proved by Bart et al., and we've mechanized this for semantics as well.
Thank you. I have a very naive question. I've heard of so many SLH variants that it's hard to keep track of. Here you see that you have a relationship, you have a generalization of two of them. How much variety do you think there are in SLH variants? At which point can we just relate them, or this is just a whole variety of non-comparable passes?
So I guess I haven't really thought about that too much before. So for one, I'm mostly familiar with the original SLH as first implemented in LLVM, the two I presented here, and strong SLH as well, which sort of was a predecessor of the ultimate SLH. I guess you could certainly conceptually systematize that a bit. Like there's just questions of tracking misspeculation is the same across all of them, and then they really only differ in what instructions they actually mask. For loads where they mask, like do you mask the address or do you mask the value? And then with selective and flexible SLH, there's the question of do you mask always or do you have some mechanism to restrict that? Yeah.
No, that's helpful, thank you.
And maybe the next speaker can start getting ready.
So you said for the future work you want to do this for other spectral variants. I was thinking about the same thing, like SLH for other spectral variants, and the hard thing is basically to create the mask, right? So for indirect branch targets, I had an idea where you could mask by, you know which address you jump to, right? If you always have the indirect branches jumping on the same register, you could take that register to make the mask out of. I'm not sure if this is something, I was wondering, for return addresses, I think it's not that easy. So I was wondering if you have another approach or a similar one.
So I guess I can, is my mic still on? Okay. The first thing to say, with these indirect branch targets and return addresses, is you already need to rely on some extra hardware features to restrict that at all, right? So you have the issue of you always need to update your mask after you perform the jump. Once you're actually in the target, before you don't know where you will be jumping. And the downside is if you cannot restrict at all where you can end up, you have no way of actually putting that check anywhere, because you can jump at arbitrary instructions and even misaligned. There might not even be an original instruction there. So you rely on hardware features such as Intel CET, and that then automatically also gives you some protections for return addresses as well. So I think we'd be in line with other related work there to say we mostly trust the hardware protections for return addresses. And so for indirect branch targets, it's just that the hardware protections are too coarse. They just give us that we jump to some defined entry point, but not where. But also, you're fully correct about if you have some register that you always jump to, you can directly use this information to track that.
I think it's time to move on to the next talk.
All right, you good? We're good. OK, so let's keep on going with the theme of hardware vulnerabilities. This time, I'm going to be talking about some fault attacks and just a little bit of side channels. So I'm Sebastian. This work was done as part of my PhD, so the co-authors are my advisors. All right, so I'm going to jump straight into it with some fault attacks. OK, so fault attacks is all kinds of attacks where you disrupt the hardware on purpose. Sorry. Oh, my bad. Thank you. We disrupt the hardware on purpose in order to create incorrect executions. These are very powerful attacks. Anything that can break will break. You can have instructions getting skipped, cache entries being corrupted, math being incorrect. Anything can happen. But when you look at this in a principled manner, there are still countermeasures that you can use to make the attacks more difficult, and some of them rely on software. And when they do, typically, because of the low-level nature of the attack, they require software to use very precise assembly code with non-functional purposes. And non-functional things can be computing the same value multiple times, double-checking your control flow, cleaning up secrets after use, and so on and so forth. Now, I don't need to tell you, but I will tell you anyway, that if you try to run this kind of code through a compiler, the compiler will ruin your day. So here's an example. Yeah, because the main problem is it's all semantically unnecessary. And we've seen the memset example before. If you write memset like this, to memset an array that you're done using, the store is dead, and therefore the program is semantically equivalent to nothing. And compilers like to output nothing. If a compiler can output nothing, it's the preferred option every single time. So what do we do? Well, what we do is kind of subtle, is we trick the compiler into not doing what it is legally entitled to do. Yeah. So what we do, we try to trick it into not realizing this is a memset. So what we do, we try to call memset to a function pointer. Yeah. Of course, semantically, this is a nothing burger, and the compiler calls the bluff and still generates nothing. Yeah. So what we can do, we can make the function pointer volatile. Magic keyword comes in, and suddenly it works. You get a function call. But if you look at the specification of the C programming language, what you realize is that this is actually equivalent semantically to reading the pointer but not calling it. So we still have problems, right? The status quo is that we make the compiler our enemy, and then we get subtle bugs if it's Tuesday and the compiler is smart. And also, we have no formal guarantees that it works, because we have formal guarantees that it shouldn't work. So how do we fix that? How do we try to make security code like this a feature of a compiler and not an accidental bug? So here's my question. How do we preserve and compile non-functional properties? And I'm interested in implementing it in LLVM. So the main idea here is to wrap the non-functional properties, the security primitives, in such a way that breaking them would constitute a semantic breakage. And then we can rely on the compiler's existing guarantees of semantic preservation to argue that security is preserved. And the idea behind this is that this avoids us having to change every single optimization to make sure that it respects our new security contract. Instead, this sort of wrapping will let us focus on the program's representation and the lower rings, which is more viable to work with. Now, I mentioned in LLVM, right? I'm not looking for the cleanest, most elegant theory here. I'm looking for the most executable result. And so there are two subtleties that come with using a production compiler like LLVM. The first one is that LLVM, goes through a lot of stages in compiling programs. You get basically 4 or 5 different languages, depending on how you count. All of them have their own semantics. And so all of them have their own non-functional things. So the specification for your security properties will vary along the compilation chain, which is a bit harder to deal with. Another subtlety, which is to our advantage this time, is that LLVM doesn't really implement the specification of the C programming language in its purest form. It's predictable in many places, and it also has a lot of extensions that constrain the behavior of the compiler more than the spec requires. And relying on this, fair game. Anything that's maintained and that works is fine, and upstream LLVM definitely is. Right, so that's the pitch, that's the objective. Now, how do we deal with this? And this is the last component that I didn't explain in the title. Tracing LLVM, that's just a name. It's the name of the compiler extension that I work on, which is, you can think of it as a prototype secure compiler for this kind of security countermeasures. And since I might forget, this will lead you to the code, the docs, and the tests. Now, how do we make LLVM preserve and compile our security code? 2 big ideas. First one is opacification. That's how we're going to hide things from the compiler in a semantically relevant way. The second is tracing. That's how we're going to connect the high-level source code with its annotations with the low-level codes where we actually want to transform the program for security. So I have one slide and one example for each of these. So let's start with opacification, right? I didn't come up with this. This is a key concept from the PhD thesis of Sun Tuanvu from a couple of years ago. And the idea goes like this. Let's say I have x equals 73, and I don't want the compiler to constant propagate it. One way that I can hide the value 73 from the compiler is by processing it through an opacification function here. And the point of this function is that it's going to be the identity, so the semantics of the programs are unaffected, but we declare the function as implementation defined. So we tell the compiler it could be anything. And because of this, the compiler is forced to perform only optimizations that would be valid for all implementations of the functions. Otherwise, it's semantically incorrect. So for instance, the compiler cannot replace x with 73 because that would be invalid for the implementation of opacify that does +1. Right? So this is how we semantically wrap our compilation constraints. And it's a fairly natural idea, so I extended it in tracing LLVM by adding primitives for opacifying computations, where you tell the compiler what values you're working with, but you don't tell it what you're computing. Addition, subtraction, multiplication, could be anything. And also one primitive for opacifying types that I won't be talking about too much. So yeah, opacification, how does that help us? Here's an example, right? One thing we like to do when we compile countermeasures for these kinds of attacks, we might have some kind of data that we want to keep track of, like, I don't know, the sandbox base address from this morning. And we want that to be in a single register because it's convenient. So we'd like to allocate all the Lagranges of a source variable to a single register. And so here's how we can do that. Ignore the first line for now. It's going to be clear in the next slide. It's int x. And we tell the compiler we're going to do something special with the writes to x. So then I have two writes, x equals 73, x equals 0. And normally, if you do that, the first write is dead, so it shouldn't occur. And the second write might occur in a different register because it's a new Lagrange. However, with opacification, what we can do is we can take these store instructions associated with the assignments and hide them from the compiler. And this little snippet here, I mean, not easy to read if you've never read LLVM-IR, but basically this is a single instruction. This is the opacification instruction that I added. And it has this instruction, this store, hidden inside itself, which is not something that you're normally able to do with LLVM, but I was able to implement that using LLVM's internal API contracts. And so what this does is that the compiler sees just a black box that takes the same parameters as before, but has no specified semantics. It could be any instruction. So the compiler cannot perform optimizations related to stores. And due to other side-effecting things, it cannot remove them either. So the opacification preserves all the stores with the right values in the right order. And then when we reach the backend, there is a register promotion pass that's added in tracing LLVM just before register allocation, which allows us to promote the stack location to a register. And when we do that, we can choose that all of the Lagranges go to the same register. So we end up here with 2 immediate loads into the same register, which means that the load of 0 indeed erases the load of 73, which would not be obvious from the semantics of the C program at the top. All right. That was opacification. Now let's talk about tracing. Tracing is the idea that the source code doesn't tell you everything you want to know about the program. There's a lot of work happening between the source code and the assembly code. That's called the compiler. And so what we want to do for security is we want to track aspects of the source code all the way down to assembly so that we can verify that things are correct or just even implement the transformations late. Basically, this tracing idea is like debug information. But unlike debug information, if an optimization threatens to render the debug info invalid, the tracing info invalid, then the optimizations will be blocked instead of destroying the debug info. So yeah, that's a guaranteed connection between the source and target code is the big idea. So that's a bit more exploratory. I still have no idea exactly what a good set of tracing primitives is for implementing security countermeasures. So right now in tracing LLVM, I have 2 of them. One for tracing the data flow of values. It's almost always going to be used to trace secrets. So we've seen, I think, about 150 of them today. And then one for tracing writes, which is what was on the previous slide, where we can tell the compiler that all the assignments to an AL value should behave exactly as in the source code. It's a way to tell the compiler that the variable in the source code has to be a storage unit in the assembly code and not just an abstract notion of the mathematical value. All right, so how does that help us writing countermeasures? Well, let's go back to cleaning up things. Where's Pierrick? Yeah, there. Now, zeroing memory is something you would do with a function call, memset, or something similar. Zeroing variables, obviously, a bit more annoying. So here is the pitch. We want to clean up all the registers at the end of a function that have held sensitive data or things that depend on sensitive data. And there's a few reasons you would do that, but mostly side channel resistance. So here's how you do that in tracing LLVM. A bit of a mouthful, but we can see that. Let's say I have 2 secrets that are global values, secret 1, secret 2. I use this annotation there. The bang is a type constructor, and then the attribute asks the compiler to trace the data flow of this variable. And this is just a way to tell the compiler that this is all secret. And then let's say I have a code that has returned secret 1 plus secret 2, for instance. What I want in the assembly code is I'm going to have 2 loads of the 2 secrets in 2 different registers, A0 and A1. And then I'm going to return an A0, so I do the add with A0 as the target. But before I return, I want to wipe A1 to make sure that I return only the return value that was intended and no other secret-related things. And this works because asking the compiler to trace the data flow means that the compiler will maintain a sort of permanent state analysis through the entire compilation chain. And then when we reach the backend, we can just ask the compiler, hey, please tell me all of the registers that are traced. So you can see how we go from a traced C variable to a traced register in assembly. That's the core idea of tracing that connects the two languages. All right. The actual sort of benchmark on which I've evaluated all this is a verify pin function, the kind you've seen 1,000 times, where I stacked 4 simple countermeasures, 2 source countermeasures for data flow and control flow integrity, so doubling the loads from memory and some kind of checkpointing, and then 2 countermeasures at the assembly level, which is not putting sensitive data on the stack and zeroing registers at the end of the function. So I'm not going to go into more details in this, but basically what I claim is that I looked at the assembly code and it's secure, so basically it works. Yeah, I mean, the code would barely fit on the slide, but who cares? The big idea is that we managed to implement multiple countermeasures at different levels of abstractions while connecting the source and target codes, which even on an example of this scale is somewhat remarkable. And also, we can activate all optimizations and nothing happens because, again, opacifications provides us with semantic guarantees. All right, I want to conclude a bit quickly, but I will just show you this slide. I think secure compilers are a little less compelling if you don't have an actual binary that you can actually execute. So I want to pitch not just the ideas of tracing LLVM, but the tools themselves. And so I feel obligated to be honest about the state of the code because you know what they say about research projects. So yeah, like many things presented today, this is a bit of a work in progress, but it's more than just a hacked demo. So talk to me if you think this might be useful to you. I just want to mention one thing. The docs for tracing LLVM include a lot of sort of onboarding info, generic info about how to use LLVM with the GNU toolchain and other things like this, because I expect that PhD students will be looking at it and they might not already know. All right, let's recap just all that. Oh, before I forget, yeah, some future work. Where do we go from there? What I've showed you is basically all of the primitives that are interesting LLVM right now. It's not a lot. The first order of business is consolidating that with more tests and implementing something that was in Santwenvu's PhD thesis that I don't have yet, which is sort of translation validation, like checks between each passes that nothing has broken. There we go. And then some things that I'm interested in is that this set of primitives allow you to better control the way that the compiler compiles the program. And it might not be useful only for security. That's an open question. I like to test that, for instance, for debugging info performance or things like this. The big issue is finding out what kind of security primitives you would have to put in the compiler to write security countermeasures. What's a unifying sort of security language for the compiler that would be useful? That's a big question. All right, so what did I say? I talked about basically just 2 features, opacification and tracing in LLVM. But the underlying message, hopefully, is that these are good foundations for fitting security in a production compiler, which would be exciting. And these are the links again. This will lead you to these slides, which have all the links. And that's it for me. Thank you.
Hello. Thanks for the talk. I have a question about, I think it was on slide 2 in the opacify function from like when you opacify 73 or something. Yeah, right. So do you declare this function as like pure? Like could it have side effects?
Wow. I think there's an entire chapter in my thesis about this. Yeah, so basically you can do a lot of variations, and depending on the variations that you do, you get more or less threats to the correctness. The original function in Santwenvu's thesis is pure, and I was a bit spooked by a lot of the problems that you can have with pure functions. There's a bunch of them with completely crazy C code where it breaks. So my version is side effecting, but I think there are situations in which you can use the pure one. I'd like to go into more details and understand this better. But yeah, my knee-jerk reaction is just side effect everything, and then you have more guarantees.
All right, thank you.
So just quickly, just for the tracing,
yes,
can that sometime on its own have overhead? Performance overhead?
Yeah, there could be overhead in missed optimization costs.
Yes.
The big problem is, actually, maybe that's something I could evaluate. One part I didn't mention is the performance cost of all this, because it's really, really, really hard to decouple the performance cost of the opacification and tracing methods from the performance costs of the countermeasures that you implement with it. In this case, yes, the one cost from tracing is going to be the missed optimizations, but you could argue that since the optimizations would have been unsound security-wise, right? You have to decouple the optimizations that you really couldn't do security-wise from the ones that you just didn't do because the formalism didn't allow for them, even though you could have done them. And I don't know how to evaluate that.
To go back to the question about pure, to go back to the pure functions thing, how hard was it to convince LLVM that your opacification operation was non-deterministic? Is it something that is easy to do, or did you have to work for it?
No, it's pretty easy. So if you do side effecting, you have something stronger than non-deterministic. And if you don't want non-deterministic, you have other attributes you can put on built-ins that are also relevant. No merge, no split. You can get something equivalent. I don't think there's something that exactly means non-deterministic, but you have equivalent things that are fairly easy to get through. All right.
Okay, let's thank the speaker again.
J'ai pas le drive.
C'est moi qui ai la moins bonne chance. Can you hear me? Yeah.
Okay, so we have another change in the program, but now Pierre Vilquet is going to talk to us about the formal verification of a RISC-V processor.
That's right, thank you. So yeah, we'll talk about some work we've been doing for the past few years about doing formal verification of processors. All right. Okay. So what are we going to do? Okay, so we have computer systems with software about which we prove some stuff. And ultimately, this software will run on hardware, and we want this hardware to be secure too. Okay, so eventually we have to look at the hardware. So that's what we're going to do. In particular, here we are going to implement and prove security properties of the hardware at the microarchitectural level. Okay, so below the assembly level. How are we going to do that? We use a hardware description language, which is COICA, which is embedded in the ROC proof assistant. In that language, we take a 32-bit RISC-V processor and implement some security mechanisms on top of it, and then we prove some properties about this. And I will show you how we do that, relying on an SMT solver for automation of the proofs. Okay, let's go. So the COICA language is so from this paper in PLJ20. It's a hardware description language which describes a hardware circuit, and it comes with a formally verified compiler from COICA to Verilog, which is a more standard HDL, hardware description language. And from here you can do whatever you want. You can simulate, put that on an FPGA or even ASIC if you want to do so. So what does COICA look like? It's a bit of an unusual language, even for hardware description language. It consists of a set of rules, which are some components of your hardware circuit. And each of those rules either executes entirely or not at all during a single cycle. Okay, all rules are going to attempt to execute, but we'll see there are some conflicts that make that sometimes a rule is cancelled. Okay. What do those rules do? They read and they write in register. This is the storage unit in COICA. And so a design is a set of rules that are ordered by what they call a scheduler here, the order in which the rules should appear to execute, even though it's hardware, so they will all execute in parallel. Okay. So just to precise a bit what the atomic here means that if there's a conflict between two rules, for example, they try to access, to read, or maybe more to write to the same register during the same cycle, then that's a conflict that can't happen. Okay, and the later rule, okay, the rule that does the second write to the register is cancelled entirely. Not only this write to the register, but all the effect of that rule. Okay, so that makes the semantics of COICA quite complex and hard to reason about. So just a small example to show you this complexity here with a simple dumb circuit here with two rules, rules A and B. Okay, rules A and B who perform writes on registers R1 and R2 under some conditions. To reason about this, we need to know what the values of the registers at the end of the cycle should be, and in particular, we need to know whether rule B executes or not, if there's a conflict or not. And there's a conflict in all those three conditions. Basically, there's a conflict. You can't do the read here if on R1 if there was a write here, so under condition cont 1, and etc. So for this small example, the conditions are already quite involved, and in a real processor pipeline, the conditions grow a lot more. Okay, so that's complex. So to solve that problem, we had a paper in CSF23 where we want to do some proofs about COICA circuits because we have a processor and we want to do some proofs about its security. Okay, so directly on the COICA circuit, we can't do that because it's too complex. ROC takes hours to do any tactic, and it's not usable. Okay, so what we do is we compile COICA circuit into what we call an IRR, an intermediate representation for reasoning. Okay, so basically, this representation will give for each register its final value at the end of the cycle as a function of the values of the registers at the beginning of the cycles. Okay, so I give you an example here for the rules we saw earlier on for each of the two registers. So we can see in particular the final value of R2 is a big conditional and whether the rule B has a conflict or not. So it grows a lot even for a small example like that. So it's better than before because here we have all the conflict information explicitly, but it's still too large and not usable directly. So what we do is we compile this IRR further using tactics that the human prover has to use interactively, so as to simplify this intermediate representation on and on until we reach a point where the representation is simple enough so that ROC tactics actually, I mean, the prover is able to perform the proof in ROC interactively. Okay. Once we have our property here, we're happy because these tactics here are verified. Well, the property holds on the IRR number n, but it also holds on the number 1 and on the Koika circuit eventually. Okay, good. Using that methodology, we took the RISC-V processor that came with the Koika language and extended it with a bunch of extensions, security mechanisms, and security mechanisms. So we extended this processor and with privilege levels. Okay, our processor is able to run in a machine with the machine privilege, or very privileged, or the user privilege for processes. We had PMP, which is physical memory protection unit. So it's protection, but on the physical memory. It's not an MMU, it's just an MPU. In ARM, they call that an MPU. We had the support for traps and two things related to control flow integrity, which are a shadow stack, a hardware shadow stack, and landing pads. And for each of those extensions, we do some proofs that, for example, if we have a memory access that violates the PMP, we access a memory region that we're not allowed to access, then we have an exception that's raised. Okay. Going back to how we prove stuff, actually this long chain of, okay, so here we go from 1 to n, but n could be hundreds. Okay, we could have hundreds of tactics to call, and it's a manual work and it's tedious. Okay. What we want to do is automate all this this part, because every time we change the processor, the Koika circuit here, well, we have to at least adapt all that, and we don't want to do that. Okay, so what we do is instead we encode our problem, the IRR, into an SMT problem, and we encode the property that we prove also as a into the same SMT problem, and then the SMT solver does all the hard work for us, and it does it quite well. Okay, a proof where ROC took minutes maybe to just QED is solved in seconds by the SMT solver. Okay, so it's very nice to for the implementation proof cycle. Okay, it's much more interactive. Okay, good. One particular security mechanism that I want to talk about, which is work in progress, is landing pads. So someone talked about that earlier today. Landing pads are instruction to enforce some part of control flow integrity, namely the integrity of function pointers, okay, indirect jumps. Okay. So the idea is you have a specific instructions that should be present at the target of those indirect calls. Okay. So that restricts the set of valid jump targets. And this mechanism is interesting because it's really at the interface between software and hardware. It requires hardware support, okay, to implement this landing pad instruction. So it's basically a no-op, okay. But also at the hardware level, you also need to ensure that when you do an indirect call, you actually land on a landing pad. Okay. And we have that proof about the Koika implementation. What we are doing also from the software side, we need some programs that are compiled with the support for landing pads. Okay, so we need to modify the compiler so that it introduces landing pads at the appropriate locations. Okay, so we do that in concert, and we want to prove several things about this transformation. First, that it's correct. Okay, so inserting the landing pads does not modify the semantics. Okay, so that's quite easy because the landing pad instruction is actually a no-op. Okay. But we also want to do a security proof, and that's in progress. Security proof says, well, when you do an indirect jump, you actually jump on an appropriate landing pad. Okay. I say appropriate because the landing pad may contain a label that identifies a proper landing pad for each call site, for example. Could be a different landing pad instruction. Ask me later. Okay. We also want to make our proofs more modular than they are. So far, we send the whole clock cycle to the SMT solver and ask properties about that. So we might want to do proofs for a given rule only. Okay, but if we do that, it's a bit tricky because sometimes we want if there's a rule that's in charge of a security mechanism, we need to prove also that this rule that does the security is not cancelled, actually runs. At least sometimes. Okay, so that's a challenge that we have to overcome to do that soundly. Okay. So to conclude, yeah, we have RV, which is a RISC-V processor with a bunch of security mechanisms, and we do proofs on those security mechanisms using an SMT solver. Okay, next proofs will be more modular. Oh yeah, one thing I want to mention is the RISC-V processor that we have is we don't have the proof that it's a RISC-V processor right now. It's a processor, but so what we would like to do is to prove that it actually implements the RISC-V semantics, for example, using the specification in Salle. Okay. And later on more security mechanisms, and we'll see which we end up doing exactly. Thank you.
Thank you. I have a question about one of the earlier slides where you added all of the IIR 1 to N.
Yeah.
Yeah, so on the slide before that, you had shown us that the logic for the conflicts was quite complicated, and I was expecting some sort of exponential complexity with the full design.
Mm-hmm.
And then suddenly you apply a series of automated treatments, and it's now all gone? What happened? Does the series of tactics just resolves all of the conflicts?
What is all gone?
Well, after all the tactics here on the diagram, you have proved trivial.
Yeah, because all the tactics here will do something like, if I take that, perhaps one of the tactics says, if conflict is true, then, I don't know, cond1 is always true, and we can replace some stuff.
Right, okay, great.
So the tactics are something like we can prune, okay, maybe we don't care at all about the value of R1. Oops. Good. I also don't have a mic. Okay. I stepped here, if that's any useful info.
Interesting.
The tactics are, something like prune, something like constant folding, and so on.
Right, so you do get to simplify away most of the complexity.
Right, yeah.
Great.
Don't step on the cable.
You mentioned this SAT solving step. So what kind of goals is actually offloaded to the SMT?
What kind of goals?
What kind of goals is offloaded to the SAT solver?
So the property the properties we prove here are about one cycle of the processor. Okay, given the initial state, properties about the initial state at the beginning of a cycle prove that it ends up in some state, right? So does that answer your question, or? Yeah. Okay.
Yeah, just a very small question. You're proving properties about one state, but if your precondition is sufficiently weak, doesn't that automatically lift to a safety property about traces for arbitrarily many cycles, or is there some issue with lifting that proof?
I'm not sure I got the question.
So your property is about one clock cycle.
Yeah.
But what stands in the way of having a theorem that's about n clock cycles?
So really, so the use of SMT here really applies well because it's we encode the input-output relation of one cycle, and we can query pretty much what we want about that to the SMT solver. It's fine. If we start to have to give the model to give to the SMT solver the model of n cycles, the problem will become huge, and I'm not sure it will scale. Okay, but in the ROC part, I think we can. Discharge most of the obligations to this and the solver, and in the ROC part have a reasoning about n cycles.
Yeah, some automatically lifting of one cycle implies n cycles, right?
Okay. Why does COICA allow possibly conflicting rules?
It's it's not an error to have a conflict, right? It can be used to model processor stalling. Okay, when you have one rule that does something, and meaning that, for example, if you write to a register, you want other rules that potentially read that register not to run for this cycle.
Right, but if I understand the semantics, it says something like you're just gonna drop the later ones. So like it sounds like in a processor like conflicts shouldn't happen, and if there is a conflict, then something is wrong with your design. Do you have to rule out conflict as part of your?
No. Again, conflicts are part of the normal life of the processor.
Okay.
It's perhaps it's a poor choice of words naming, but no. Conflicts can happen, and they happen conditionally, so they don't happen at every cycle, presumably, hopefully.
Okay, so I think we can thank Pierre again.
attended. So I think you can, we can be happy about this workshop. We can even applaud ourselves. And more important announcement, for dinner, it's gonna be at 7 p.m. at Crêperie Les Pieds de Blé. So the address is here. If you didn't register but would still like to come, it's possible. Let me know so that I can somehow tell the restaurant how many more people we expect. Hopefully not 50, he told me that's too much. And so it's kind of straight south, and then we cross this river here that we see, and then the restaurant will be there. So thank you, and see you at the restaurant.